Somewhere out there in the vast darkness of space, invisible forces twist and ripple with enough power to tear stars apart. These are the universe's most extreme magnetic fields, cosmic giants so strong they can bend reality itself. Picture a force so intense it warps the paths of particles traveling at nearly the speed of light, or shapes entire galaxies into swirling masterpieces across millions of light years. What you're about to discover isn't just science, it's a hidden symphony of power, written in the language of magnetism, playing out on scales so enormous they defy human comprehension. Think about the last time you held a simple refrigerator magnet. That tiny pull you felt is a whisper compared to the cosmic roar of magnetic fields in space. Around neutron stars, these forces ramp up to strengths 1 trillion times stronger than Earth's, enough to stretch atoms into thin threads or wrench electrons from their orbits. Even black holes, the universe's ultimate destroyers, can't escape their influence. Magnetic fields sculpt the jets of superheated plasma that blast from these monsters, shaping some of the most violent and beautiful phenomena we've ever observed. This isn't just about raw power, though. These magnetic marvels hold secrets to how stars are born, how galaxies evolve, and perhaps even how the universe itself got its structure. They're the invisible architects of the cosmos, hiding in plain sight, and today we're pulling back the curtain. From jarring stellar explosions to the eerie quiet of magnetars lurking in deep space, you're about to witness 50 facts that'll change how you see the universe. Buckle up, we're diving into extremes where the rules of physics as we know them start to bend. Even among the most extreme objects in the universe, magnetars stand in a league of their own. These remnants of dead stars pack a magnetic punch so intense it defies imagination, fields 1 quadrillion times stronger than Earth's, powerful enough to erase your credit card from halfway across the solar system. Born in the chaotic aftermath of supernova explosions, magnetars are neutron stars that spin at dizzying speeds, their cores crammed with matter so dense a single teaspoon would weigh billions of tons. But it's their magnetism that truly sets them apart. When a massive star collapses, its magnetic field doesn't just vanish, it gets concentrated, twisted, and amplified into something monstrous. The result, a magnetar's pull is so fierce it warps the very fabric of space around it, creating distortions that can be detected light years away. Scientists spot these cosmic powerhouses through their telltale X-ray and gamma-ray flares, bursts of energy so violent they briefly outshine entire galaxies. Sometimes the crust of a magnetar cracks under the strain, triggering starquakes that ripple through space-time and send shockwaves of radiation across the cosmos. One of the most terrifying displays of a magnetar's power happened in 2004, when a flare from 50,000 light-years away temporarily ionized Earth's upper atmosphere. If that explosion had occurred within 10 light-years of us, it could have stripped our planet's ozone layer bare. Yet these destructive forces also sculpt the universe in unexpected ways. Magnetars may seed space with heavy elements, their magnetic fields acting like cosmic forges where atoms are crushed into gold, platinum, and other rare metals. They're not just destroyers, they're hidden architects, shaping the universe one cataclysmic pulse at a time. Among the countless magnetars strewn across the cosmos, one particular monster reigns supreme: SGR 180620. This cosmic powerhouse holds the record for the strongest magnetic field ever measured, a staggering 10 quadrillion times more intense than Earth's. To put that in perspective, if you could somehow survive getting within 1,000 miles of this thing, its magnetic grip would rip the iron from your blood. But SGR 180620 didn't just earn its fame by lurking menacingly in space. In December 2004, it unleashed a gamma-ray burst so violent it rewrote the rules of stellar outbursts. For a fraction of a second, this single magnetar outshone the entire Milky Way, releasing more energy than our Sun emits in 150,000 years. The pulse of radiation was so powerful it bounced off the moon and lit up Earth's upper atmosphere like a cosmic flashbulb, momentarily altering its chemistry. Satellites in orbit actually shut down to protect themselves, while radio blackouts rippled across the planet. What made this flare truly terrifying was the distance. SGR 180620 sits 50,000 light-years away, far beyond our galaxy's core. Had it occurred within just 10 light-years of Earth, the blast would have stripped away our ozone layer, triggering mass extinctions and bathed the planet in deadly radiation. Yet for all its destructive potential, this magnetar also offers scientists a rare window into the extremes of physics. Its eruptions behave like nothing else in nature, twisting Einstein's theories and challenging our understanding of how matter behaves under pressures and forces that simply don't exist anywhere else. Here's the eerie part: we don't fully understand why SGR 180620's magnetic field is so absurdly strong. Some theories suggest its core is a swirling ocean of superconducting fluid, amplifying the field to impossible levels. Others speculate it's the result of a perfect storm during its formation, when the dying star's magnetic lines became impossibly tangled. Whatever the cause, it stands as a humbling reminder that the universe operates on scales we're only beginning to comprehend. And somewhere out there, this magnetic leviathan continues to spin, its unfathomable power lying dormant until the next time it decides to remind the galaxy who's boss. While magnetars dominate with raw magnetic power, their cosmic cousins pulsars wield magnetism with mesmerizing precision. Picture a city-sized sphere spinning hundreds of times per second, flinging beams of radiation across space like a hyperactive cosmic lighthouse. These neutron stars may not match magnetars in sheer field strength, but their rapid rotation transforms them into unrivaled dynamos, generating magnetic forces 1 billion times Earth's while sculpting some of the most predictable rhythms in the universe. The secret lies in what astronomers call the dynamo effect. When a massive star collapses into a neutron star, its original magnetic field gets compressed into an area millions of times smaller. But unlike magnetars, pulsars amplify their fields through motion, spinning so fast they essentially become self-powering electromagnetic engines. Some rotate at dizzying speeds exceeding 700 revolutions per second, their surfaces moving at 1/4 the speed of light. This churns their interiors into superconducting soups of neutrons, where frictionless currents sustain magnetic fields strong enough to accelerate particles to near light speeds. What makes pulsars truly cosmic beacons are their radiation jets. Channeled by those intense magnetic fields, charged particles spiral along magnetic poles, releasing tightly focused beams of radio waves, X-rays, and gamma rays. Because these jets don't align with the star's rotation axis, they sweep across space like a spinning searchlight. From Earth, we detect these as precise clockwork pulses, some so regular they rival atomic clocks in accuracy. The Crab pulsar, born in a supernova observed in 1054, still flashes 30 times per second with near-perfect consistency, a metronome ticking across 950 light-years. Scientists treasure pulsars as natural laboratories for extreme physics. Their intense gravity warps spacetime so severely that orbiting them would distort time itself, a phenomenon confirmed by monitoring pulses from pulsars paired with other stars. Some even serve as galactic GPS markers. The Voyager spacecraft carried pulsar maps to triangulate Earth's position using their steady beats. And in 2017, colliding neutron stars detected via gravitational waves were pinpointed using their pulsar-generated gamma rays, proving these magnetic powerhouses can guide us to cosmic cataclysms. Yet pulsars hide eerie mysteries. A growing class of black widow pulsars vaporize their companion stars with relentless radiation, while glitching pulsars occasionally speed up without warning, perhaps from crust quakes or vortices in their superfluid cores. Each anomaly peels back another layer of our understanding. revealing how matter behaves under conditions so extreme they turn the familiar laws of physics into mere suggestions. These spinning sentinels remind us that magnetism, when paired with motion, becomes more than a force. It's a cosmic conductor orchestrating light, time, and space itself. Our sun may seem like a steady ball of light, but beneath its glowing surface rages a churning ocean of magnetism more dynamic than anything in our solar system. Every 11 years, the sun's magnetic field completely flips north, becomes south, and south becomes north in a cycle that drives some of the most spectacular explosions in our cosmic neighborhood. These aren't just abstract curiosities, they're forces powerful enough to knock out satellites, disrupt power grids, and paint the skies with auroras visible halfway across the planet. At the heart of this chaos lies a process scientists call the solar dynamo. Deep within the sun, plasma hotter than lava circulates like water in a boiling pot, twisting and stretching magnetic field lines like taffy. When these tangled lines snap, often near dark patches called sunspots, they unleash enough energy to power human civilization for thousands of years in mere seconds. The result, solar flares, white-hot eruptions that blast X-rays across the solar system, and their more disruptive cousins, coronal mass ejections. These are billion-ton clouds of magnetized plasma hurled into space at millions of miles per hour, and when one hits Earth's magnetic field, the consequences can be breathtaking or terrifying depending on your perspective. Take the Carrington event of 1859, a coronal mass ejection so powerful it sparked fires in telegraph offices and lit up the night sky as far south as Cuba. If a storm like that struck today, experts estimate it could disable GPS networks, cripple communications, and trigger blackouts lasting months. But these magnetic tantrums also gift us with the northern lights, as solar particles spiral down Earth's magnetic field lines and set the atmosphere ablaze with shimmering greens and purples. What's truly remarkable is how the sun's magnetism connects us to the wider galaxy. Solar storms can carve protective bubbles around spacecraft, while quieter periods allow cosmic rays, particles accelerated by distant supernovae, to penetrate deeper into our solar system. Some researchers even speculate that the sun's magnetic whims might subtly influence Earth's climate over centuries. One thing's certain: our star's invisible magnetic hands shape everything from your smartphone's signal to the very particles that dance overhead in the polar night. And with every flip of its magnetic poles, the sun reminds us it's not just a light in the sky. It's a living, breathing force of nature. Deep within the sun's churning atmosphere, a silent battle rages, one where invisible magnetic lines twist, stretch, and violently snap apart in a process that powers some of the most energetic explosions in our solar system. This is magnetic reconnection, the hidden engine behind solar flares, and the reason the sun's corona burns at millions of degrees while its surface stays relatively cool. Picture two rubber bands stretched to their limits, twisted together until they finally rip apart with a snap. That's essentially what happens to the sun's magnetic field lines, except the energy released is enough to vaporize entire planets. When these lines tangle, often near sunspot regions where magnetism intensifies, they don't just quietly untwist. They explosively reconfigure, converting stored magnetic energy into heat and motion at unimaginable scales. In milliseconds, temperatures skyrocket to over 10 million degrees, accelerating particles to near light speeds and launching eruptions visible across interplanetary space. The most dramatic product of this process, X-class solar flares, explosions so bright they can briefly outshine the sun's entire surface in certain wavelengths. A single one of these eruptions can release the energy of 1 billion hydrogen bombs, hurling radiation across the solar system in a pulse that reaches Earth in just 8 minutes. But the real cosmic spectacle comes after the flare, when the disrupted field lines trigger coronal mass ejections, billion-ton clouds of magnetized plasma racing outward at up to 1.6 million miles per hour. What's truly baffling is how this phenomenon solves one of the Sun's greatest mysteries: why its outer atmosphere, the corona, is hundreds of times hotter than the surface below. For decades, scientists struggled to explain how heat could defy the normal rules of thermodynamics, flowing outward from the cooler surface to the scorching corona. Magnetic reconnection provides the answer. Those snapping field lines act like invisible whips, transferring energy so efficiently they turn the corona into a furnace far hotter than the Sun's visible layer. Satellites like NASA's magnetospheric multiscale mission have flown through Earth's magnetic field to study reconnection up close, revealing how electrons get catapulted to relativistic speeds during these events. The data shows plasma particles don't just move, they surf along newly reconnected field lines like cosmic wakeboarders, gaining tremendous energy from the sudden shifts. This same process occurs throughout the universe, from the atmospheres of other stars to the jets of supermassive black holes, proving magnetic reconnection isn't just a solar quirk, it's a universal mechanism for turning magnetism into raw power. Yet for all its destructive potential, this phenomenon also plays a creative role. Some researchers believe magnetic reconnection helped shape our solar system's birth, channeling material into the young sun while distributing heavier elements outward. Today, it continues sculpting space weather around every planet with a magnetic field, proving that even in the violent snapping of invisible lines, there's an underlying order driving the cosmos forward. Jupiter doesn't just rule our solar system as the largest planet. It wields a magnetic field so colossal it could swallow Earth's entire magnetic bubble without a trace. This invisible force stretches over 4 million miles toward the Sun, forming a protective shield 20,000 times stronger than our own. If you could see Jupiter's magnetosphere with the naked eye, it would appear larger than the full moon in our sky, despite being 400 million miles away. But this isn't just a bigger version of Earth's cozy magnetic blanket. It's a chaotic, radiation-charged fortress that creates some of the most hostile conditions in our cosmic neighborhood. At the heart of this magnetic maelstrom lies Jupiter's rapid rotation. The planet spins so fast, completing a day in just under 10 hours, that its metallic hydrogen core churns like a dynamo, generating currents that amplify its magnetic field to staggering levels. This creates radiation belts so intense they deliver a lethal dose to an unshielded astronaut in minutes. NASA's Juno spacecraft, designed to study these extreme conditions, had to armor its electronics in a titanium vault just to survive periodic passes through these zones. Even then, the probe's cameras occasionally get bombarded with high-energy electrons that leave streaks in images like cosmic graffiti. What makes Jupiter's magnetic environment truly bizarre is how it interacts with the planet's volcanic moon, Io. Every second, Io's eruptions spew a ton of sulfur dioxide gas into space, where Jupiter's magnetic field ionizes it into a glowing donut of plasma called the Io torus. This charged particle highway beams radio waves so powerful we've detected them on Earth with amateur equipment. Sometimes, Jupiter's magnetism yanks electrons from this torus and accelerates them along field lines until they slam into the planet's atmosphere near the poles, sparking permanent auroras large enough to engulf Earth. These aren't the graceful northern lights we know. They're ultraviolet infernos pumping out terawatts of energy, fueled by what's essentially the largest particle accelerator in the solar system. Yet Jupiter's magnetic might extends far beyond visible light. Its magnetosphere acts like a cosmic net, snatching charged particles from the solar wind and energizing them into relativistic electrons. Some get slingshotted outward, creating shock waves that ripple across the solar system, while others spiral inward, bombarding Jupiter's icy moons with radiation that could bake their surfaces sterile. Europa's subsurface ocean might be shielded by miles of ice, but the constant particle rain creates a bizarre chemical soup on its surface, one that could hold clues about whether life might survive in such extremes. For all its ferocity, Jupiter's magnetic field is also a celestial protector. Without it, the solar wind would strip away the atmospheres of the Galilean moons and erode Jupiter's own gaseous envelope over billions of years. This balancing act between creator and destroyer, particle accelerator and cosmic shield, makes Jupiter's magnetism a laboratory for physics we can't replicate on Earth. It's a reminder that magnetic fields aren't just invisible lines on a diagram. They're living, breathing forces that sculpt worlds, steer storms, and maybe even set the stage for life in the unlikeliest of places. Saturn's magnetic field defies the cosmic norm with an elegance that's left scientists scratching their heads. While most planets, including Earth and Jupiter, have magnetic poles tilted at angles to their rotation axes, like a compass needle gone askew, Saturn's alignment is almost perfectly straight. Its north and south magnetic poles line up with near-perfect symmetry to the planet's spin, a precision so unusual it makes Saturn the solar system's oddball in magnetic geometry. This bizarre alignment challenges everything we know about how planetary dynamos work. Deep within Saturn, where temperatures soar to 11,000 degrees and pressures crush hydrogen into a metallic soup, electric currents should generate magnetism the same chaotic way they do in other gas giants. Yet somehow, Saturn's internal machinery produces a field that's not just strong, it's unnervingly orderly. One theory suggests the answer lies in helium rain. As Saturn cools, helium condenses and droplets fall inward through layers of hydrogen, smoothing out turbulence that might otherwise tilt the magnetic field. Another idea points to a thick layer of stable metallic hydrogen acting like a cosmic filter, dampening irregularities before they reach the surface. The Cassini spacecraft gave us our closest look at this magnetic enigma during its 13-year mission. Flying through Saturn's magnetosphere, the probe discovered something even stranger. The planet's magnetic field pulses with a rhythm almost perfectly synced to its rotation. But here's the twist. Saturn's rotation rate is notoriously hard to pin down because its gaseous surface lacks fixed landmarks, and these magnetic pulses don't neatly match the cloud movements we'd expect. This mismatch hints at hidden dynamics deep below the clouds, where layers of fluid might be sliding past each other like cosmic gears. What makes Saturn's magnetic symmetry truly puzzling is how it interacts with the planet's iconic rings. Charged ice particles from the rings spiral along magnetic field lines, creating unexpected patterns in Saturn's upper atmosphere. In some regions, these particles even create a faint, glowing ring of their own, an auroral necklace visible only in ultraviolet light. Yet despite this delicate dance, the main magnetic field remains stubbornly symmetrical, resisting the distortions seen around Jupiter or Earth. Scientists suspect Saturn's peculiar magnetism might hold clues to exoplanets far beyond our solar system. If gas giants orbiting other stars share this trait, it could redefine how we model their interiors and potential for harboring moons with hidden oceans. For now, Saturn keeps its secrets locked beneath swirling clouds, its perfect magnetic alignment standing as both a cosmic marvel and a reminder that even the familiar parts of our solar system still guard mysteries waiting to be unraveled. Earth's magnetic field is far more than an invisible force that guides compass needles. It's a dynamic, living shield that has guarded our planet for billions of years. Generated by the churning of molten iron and nickel in Earth's outer core, this geomagnetic fortress extends tens of thousands of miles into space, deflecting deadly cosmic radiation and solar wind like an invisible suit of armor. Without it, our atmosphere would have been stripped away long ago, leaving Earth as barren as Mars. The engine behind this protective barrier lies nearly 3,000 kilometers beneath our feet, where temperatures rival the surface of the Sun. Here, Earth's liquid outer core swirls in turbulent currents, acting like a colossal electrical conductor. As the planet rotates, this molten metal generates electric currents through what scientists call the geodynamo effect, essentially turning Earth into a giant self-sustaining electromagnet. The resulting field isn't static. It writhes and fluctuates with magnetic poles that drift dozens of kilometers annually and even flip entirely every few 100,000 years. Evidence locked in ancient volcanic rocks shows these reversals leave no lasting harm, though compasses would briefly point south until the field stabilizes again. What makes Earth's magnetism truly life-saving is how it interacts with the solar wind, a supersonic stream of charged particles constantly blasting from the sun. When these particles encounter our magnetic field, most get funneled safely around the planet along invisible lines of force, creating a teardrop-shaped protective bubble called the magnetosphere. Some get trapped in twin donut-shaped radiation belts discovered in 1958, where they spiral harmlessly until dissipating. Occasionally, intense solar storms overwhelm these defenses, allowing particles to slip into the upper atmosphere near the poles. The result, the dazzling auroras that paint our skies, nature's reminder of the invisible battle raging overhead. This shield does more than create pretty lights. By blocking 99% of solar radiation, it protects both our technology and our DNA. Satellite electronics get fried without its cushion, and astronauts on the International Space Station rely on its shadow when orbiting within its protective embrace. Even more critically, the magnetic field prevents solar wind from gradually eroding our atmosphere, a fate that befell Mars when its core cooled and dynamos shut down billions of years ago. Traces of oxygen and nitrogen ions still escape Earth today at about 90,000 tons annually, but without our magnetic guardian, this loss would accelerate dramatically. Recent discoveries reveal the field isn't just a blunt barrier, it's a sophisticated filter. Certain frequencies of electromagnetic waves pass through more easily than others, creating a natural radio window that may have influenced the evolution of life. Some researchers speculate this selective shielding could explain why terrestrial organisms rely on specific wavelengths for vision and communication. As we uncover more exoplanets, astronomers now look for magnetic fields as key indicators of potential habitability, because a world might have water and warmth, but without this invisible guardian, it could never hold onto the precious ingredients for life. Earth's magnetic field isn't just part of our planet's story, it's the silent architect of everything that breathes, grows, and thrives upon its surface. Mars stands as a planetary cautionary tale, a world that once brimmed with rivers, lakes, and possibly even oceans, now reduced to a frozen desert. The key to its tragic transformation lies beneath the rust-colored soil, the ghost of a magnetic field that vanished billions of years ago. Unlike Earth's robust shield, Mars' dynamo sputtered to a halt, leaving the planet defenseless against the solar wind's relentless assault. Clues to this ancient protection are etched into Mars' crust. Orbiters like NASA's Maven mission have detected patches of magnetized rock stretching hundreds of miles, fossilized remnants of a global field that thrived over 4 billion years ago. These magnetic stripes mirror patterns on Earth's seafloor, where lava solidifies while recording fluctuations in our planet's polarity. On Mars, they tell a story of a core that once churned with molten metal, generating a protective bubble as substantial as Earth's. Then catastrophe struck. Scientists believe Mars' smaller size sealed its fate. With only half Earth's diameter, its interior cooled rapidly. The core's metallic dynamo seized up, and without that churning engine, the magnetic field collapsed. Solar wind, a stream of charged particles racing from the sun at 1,000,000 miles per hour, began sandblasting the atmosphere away. Maven measurements show Mars still loses about 100 grams of atmosphere every second, atom by atom stripped into space. Over eons, this erosion turned a world with enough atmospheric pressure for flowing water into a near vacuum where liquid boils away instantly. The consequences were devastating. River valleys and lake beds visible from orbit prove water once pooled freely, but as atmospheric pressure plummeted, surface water either froze underground or vaporized into space. Without a magnetic shield to deflect cosmic radiation, the surface became sterile, bombarded with enough ultraviolet light to shatter organic molecules. Had Mars' field persisted, its story might have been different, perhaps even hosting life beneath protective electromagnetic wings. Yet Mars' magnetic tragedy offers unexpected gifts. Those magnetized crustal remnants create localized shields, diverting solar wind in patches and preserving traces of atmosphere in certain regions. Some researchers speculate these magnetic umbrellas could shelter future colonists from radiation, making specific zones unexpectedly habitable. And as we study exoplanets, Mars serves as a warning: size and geology matter. A world might orbit in the so-called Goldilocks zone, but without an electromagnetic guardian, it could end up just another frozen relic, a whisper of what might have been. Mercury shouldn't have a magnetic field at all. This tiny world, barely larger than Earth's moon and with a day that lasts 59 Earth days, defies expectations by generating a detectable magnetic force, one about 1% as strong as Earth. For decades, scientists assumed Mercury's core had cooled and solidified billions of years ago, rendering it magnetically dead like Mars. But when NASA Mariner 10 spacecraft first detected weak magnetism during flybys in 1974 and 1975, it sparked a cosmic mystery. How could such a small planet, so close to the Sun's blistering heat, still churn with enough internal dynamism to power a magnetic field? The answer lies in Mercury's bizarre interior. Unlike Earth's fully molten outer core, Mercury's appears to be a layered hybrid, part liquid, part solid. NASA, a messenger mission which orbited Mercury from 2011 to 2015, revealed the planet's core makes up a staggering 85% of its radius. That's nearly twice the proportional size of Earth's core, leaving only a thin outer shell of mantle and crust. This oversized metallic heart cools so slowly that pockets of molten iron still swirl today, stirred by the planet's sluggish rotation. Scientists describe it as a snowy core, where iron crystals form in the liquid outer layer like flakes in a slurry, creating convection currents that generate magnetism through a process called thermochemical dynamo. Messenger instruments uncovered even stranger quirks. Mercury's magnetic field isn't centered on the planet's core but offset northward by about 20% of the planet's radius. This lopsided field creates an asymmetric shield, with one hemisphere far more exposed to solar wind than the other. Solar particles bombard the surface near the South Pole, blasting sodium and other atoms into a tenuous exosphere that tails behind the planet like a comet's glow. Meanwhile, the field's twisted geometry funnels charged particles toward magnetic hotspots, where they trigger X-ray auroras, ghostly flashes invisible to human eyes but detectable by spacecraft. Theories abound about what keeps Mercury's core churning. Sulfur mixed with iron could lower its melting point like antifreeze, preserving liquid layers. Tidal forces from the Sun's gravity might flex the core, generating heat like kneading dough, or residual heat from the planet's violent formation, where a possible collision with another protoplanet stripped away much of its outer layers could still linger. Whatever the cause, this feeble yet persistent magnetism challenges our understanding of how planetary dynamos form and fade. Mercury's field, though weak, plays cosmic gatekeeper. It carves out a miniature magnetosphere just large enough to deflect some solar wind, creating a pocket of relative calm where atoms sputtered from the surface can linger. Without it, the solar system's smallest planet would be utterly barren: no transient atmosphere, no space weathering patterns, just a sterile rock baking under unfiltered stellar radiation. As we study exoplanets orbiting close to their stars, Mercury stands as a reminder: size isn't everything. Even the smallest worlds can harbor magnetic surprises hidden beneath their silent surfaces. Uranus and Neptune break all the rules when it comes to planetary magnetism. Unlike Earth or Jupiter, with their relatively straightforward north-south magnetic alignments, these ice giants wield fields that look like they were designed by a drunken compass wildly off-center and tilted at angles that defy logic. Uranus spins nearly on its side at 98 degrees, but its magnetic axis tips even further at a staggering 59 degrees from its rotational pole. Neptune's field is no less bizarre, offset by over 30 degrees and originating from deep inside the planet, nowhere near its geometric center. If you tried navigating these worlds with an ordinary compass, the needle would spin like it was caught in a tornado. The reason for this magnetic chaos lies in the planet's exotic interiors. Deep beneath their cloudy atmospheres, extreme pressures crush water, methane, and ammonia into a bizarre, electrically conductive slush scientists call supersonic ice. This isn't the ice we know. It's a hot, dense material where water molecules break apart, allowing oxygen atoms to form a solid lattice while hydrogen ions flow through it like a liquid metal. Unlike Earth's molten iron core, which generates our planet's magnetism through straightforward circulation, Uranus and Neptune's fields likely arise from this churning, metallic ocean sandwiched between their rocky cores and outer layers of molecular hydrogen. Voyager 2's flybys in the 1980s revealed just how strange these magnetic environments are. The spacecraft detected fields that don't just tilt, they're lopsided, with strengths varying dramatically across each planet's surface. On Uranus, the magnetic field strength at the cloud tops ranges from a feeble 1/10 of Earth's field to nearly as strong as ours, depending on where you measure. Neptune's field, meanwhile, includes bizarre localized spikes where magnetism intensifies in unexpected pockets. These irregularities suggest the dynamos generating them aren't uniform deep oceans of conductive fluid, but patchy, turbulent layers where currents twist and fragment unpredictably. What makes these tilted fields truly consequential is how they interact with the solar wind. As the planets rotate, their off-kilter magnetic fields wobble like unbalanced gyroscopes, creating magnetospheres that tumble through space in dizzying patterns. During parts of Uranus' 84-year orbit around the Sun, its rotational pole points almost directly at our star while its magnetic poles flail wildly, opening massive gaps in its protective bubble. Solar particles flood in, sparking auroras that don't neatly circle the poles like Earth's, but flicker erratically across the planet's sunlit side. Neptune's rotation, completed every 16 hours, creates a magnetosphere that twists into a corkscrew shape behind the planet, flinging charged particles into space like a cosmic slingshot. Scientists suspect these planetary oddities might be more common than we thought. Exoplanets orbiting distant stars could share similar interiors, their magnetic fields equally tilted and unstable. Some researchers even speculate that supersonic ice might exist in gas giants beyond our solar system, hinting at a whole class of worlds where magnetism follows rules we're only beginning to decipher. For now, Uranus and Neptune remain our best and strangest examples of how magnetic fields can go rogue, proving that even in the ordered cosmos, nature still has plenty of surprises up its sleeve. Spanning 100,000 light-years from end to end, the Milky Way's galactic magnetic field weaves through space like an invisible spiderweb, so faint you could break its grip with a handshake, yet powerful enough to sculpt the birth of stars and steer the most energetic particles in the universe. Unlike the concentrated fields around planets or magnetars, this cosmic tapestry stretches across the entire galaxy, its delicate strands channeling charged particles and dust along invisible highways. Radio telescopes have mapped its structure by detecting how it twists the polarization of starlight and alters the paths of cosmic rays, revealing a force both subtle and omnipresent. At its core, our galaxy's magnetism arises from the slow churn of interstellar plasma. Free electrons spiral along magnetic field lines, generating currents that amplify the field over millions of years. But what makes it truly extraordinary is its scale. Imagine a network so vast it takes light centuries to traverse its loops, yet so diffuse that its average strength measures just a few millionths of Earth's field. This faint pull becomes significant across galactic distances, like a gentle breeze that can redirect a ship given enough ocean to work with. One of its most crucial roles lies in star formation. Dense clouds of gas collapse under gravity to birth new stars, but without magnetic fields, this process would happen too quickly. The galaxy's faint magnetism acts like an invisible brake, resisting the freefall of matter and regulating how stars ignite. In the Orion Nebula, astronomers have observed filamentary structures where magnetic fields guide gas into narrow streams, cosmic rivers feeding stellar nurseries. Without this delicate balance, stars might form in erratic bursts, disrupting the galaxy's equilibrium. The field also serves as a grand cosmic ray accelerator. Charged particles zipping through space get deflected by these magnetic threads, gaining energy with each twist until they're traveling near light speed. Some galactic magnetic hotspots, like the turbulent region near the supermassive black hole at our galaxy's center, act as natural particle colliders, hurling protons and electrons across interstellar space. When these cosmic rays eventually collide with Earth's atmosphere, their paths carry fingerprints of the Milky Way's magnetic architecture, a reminder that even our planet's weather is touched by forces light years away. Yet mapping this invisible framework remains a monumental challenge. Scientists piece it together using pulsars as cosmic lighthouses. Their polarized radio waves twist slightly as they pass through magnetized interstellar clouds, betraying the field's orientation. Recent surveys reveal unexpected kinks and reversals in the Milky Way's magnetism, suggesting dynamic processes we're only beginning to understand. Some theories point to ancient supernova bubbles distorting the field, while others invoke large-scale flows of gas from the galactic halo. What's clear is that this fragile yet far-reaching force connects every corner of our galaxy. From guiding stellar births to etching patterns in interstellar dust, the Milky Way's magnetic field proves that even the faintest influences, given enough space and time, can shape the universe in profound ways. Hidden within distant clouds of gas and dust, magnetic fields act as invisible sculptors, guiding raw cosmic material into the fiery hearts of newborn stars. The famous pillars of creation in the Eagle Nebula, those towering cosmic spires photographed by Hubble, owe their breathtaking shape to these unseen forces. As gravity pulls gas together to form stars, magnetism resists the collapse like a cosmic safety net, slowing the process and creating intricate structures that wouldn't exist in a purely gravitational universe. Picture a vast molecular cloud, light years across, slowly contracting under its own weight. Without magnetic fields, this gas would collapse chaotically into clumps, forming stars randomly like popcorn bursting in uneven heat. Instead, magnetic field lines thread through the cloud like cosmic guitar strings, channeling ionized gas along their length. Where these lines bunch together, they create dense filaments, stellar nurseries where gas flows like water through magnetic canyons. The pillars of creation showcase this perfectly. Their finger-like projections aren't just random shapes, but gas compressed between competing magnetic zones, with fledgling stars glowing at their tips where matter finally overcomes magnetic resistance. This tug-of-war between gravity and magnetism explains why stars don't form all at once. Fields strong enough to support their own weight against gravity create what astrophysicists call magnetostatic support, essentially magnetic pressure putting the brakes on collapse. Only when enough gas accumulates to overwhelm these forces does fragmentation occur, breaking the cloud into smaller, star-forming cores. Observations of the Orion Nebula reveal this drama in action, with dust grains aligning like compass needles along magnetic lines, tracing patterns visible in polarized light. The process leaves behind cosmic fingerprints. As protostars spin up during formation, their magnetic fields whip surrounding gas into towering jets called Herbig-Haro objects. These plasma fountains, sometimes stretching light years into space, carry away excess angular momentum that would otherwise prevent the star from condensing further. Without magnetic fields slinging this material outward, many stars might never achieve the dense cores needed to ignite nuclear fusion. What's truly remarkable is how delicately balanced this system is. Too much magnetic resistance and star formation grinds to a halt, too little and clouds collapse into formless blobs. The pillars of creation embody this precarious equilibrium, their majestic forms slowly evaporating under nearby starlight even as new stars emerge within them. They stand as proof that the universe's grandest structures often owe their existence to forces we can't see, sculpting chaos into beauty one magnetic thread at a time. Supermassive black holes like Sagittarius at the Milky Way's core aren't just gravitational monsters, they're cosmic power plants, harnessing magnetism on scales that dwarf entire solar systems. These behemoths don't simply swallow matter, they transform it into blazing jets of particles that streak across space at nearly the speed of light. And the secret behind this incredible acceleration lies in twisted magnetic fields stronger than anything in our galaxy. Picture an enormous cosmic whirlpool where gas and dust spiral toward the event horizon in a superheated disk called an accretion disk. As this material churns at millions of degrees, electrons get stripped from atoms, creating a seething plasma. Here's where the magic happens. The black hole's immense spin drags spacetime itself into a vortex, twisting magnetic field lines into tightly wound coils. These aren't passive lines of force, they're dynamic whips snapping with pent-up energy, channeling particles into narrow beams perpendicular to the disk. The process resembles water spiraling down a drain, then shooting back out through a pair of fire hoses. Event Horizon Telescope observations reveal Sagittarius A's magnetic field structure in unprecedented detail, showing how these fields organize chaotic inflows into orderly outflows. Some particles get flung outward just before crossing the event horizon, surfing magnetic field lines like cosmic roller coasters. The resulting jets can stretch for thousands of light years, carrying energy equivalent to millions of supernovae. One such jet from galaxy M87, imaged in 2019, stretches 5,000 light-years, a celestial searchlight powered entirely by magnetic mayhem. What's truly remarkable is how black holes recycle their fuel through these magnetic mechanisms. Not everything that falls toward the abyss gets consumed. Up to 40% gets catapulted back into space, enriching surrounding galaxies with heavy elements and regulating star formation. Without this magnetic recycling, galaxies might exhaust their gas too quickly, leaving the universe devoid of new stars. Even more astonishing, these jets can trigger star birth in distant gas clouds. They collide with meaning black holes, often seen as destroyers, can also be creators on a galactic scale. The latest simulations suggest these magnetic processes might explain why some supermassive black holes flicker like cosmic strobe lights. As magnetic loops snap and reconnect near the event horizon, they create bursts of energy observable across the electromagnetic spectrum. Some researchers speculate that gravitational waves from colliding black holes might even carry imprints of their pre-merger magnetic fields, clues to how these invisible forces shape the most violent events in the cosmos. Yet mysteries remain. How exactly do magnetic fields extract energy from a black hole's spin? Why do some jets pulse erratically while others flow smoothly? Each observation peels back another layer, revealing magnetism as the hidden hand guiding some of the universe's most spectacular light shows. Far from being dark, silent killers, black holes with their magnetic might are some of the brightest, most dynamic engines in creation, proof that even in the darkest corners of space, invisible forces still rule supreme. Quasars outshine entire galaxies by converting the fury of supermassive black holes into blinding torrents of light. and magnetism is the invisible conductor orchestrating this cosmic fireworks show. These brilliant beacons, visible across billions of light years, rely on magnetic fields to transform chaotic infalling matter into the most efficient energy factories in existence. At their core lies the same mechanism that powers smaller black hole jets, but amplified to staggering extremes. Magnetism so intense it bends space itself into a particle accelerator. Picture a black hole weighing billions of suns, its gravitational pull tearing apart stars and gas clouds. As this material spirals inward, it forms an accretion disk hotter than the surface of a million stars. Here, magnetic fields emerge as the ultimate puppet masters. Turbulent motions in the ionized plasma stretch and twist magnetic field lines like rubber bands, storing immense energy until snap. They break and reconnect in explosive events called magnetic reconnection. These bursts launch particles to near light speeds while funneling material toward the black hole's poles, where twin jets erupt with enough power to pierce through entire galaxy clusters. The numbers defy belief. A typical quasar converts up to 40% of infalling mass directly into energy, far surpassing nuclear fusion's meager 0.7% yield in stars. This outrageous efficiency comes from magnetism's ability to extract rotational energy from the black hole itself, a process first theorized by physicist Roger Blandford in 1977. As the black hole spins, it drags spacetime around it like a whirlpool, winding magnetic field lines so tightly they act as cosmic transmission belts. Particles surfing these lines gain colossal energy before being flung outward in jets that can stretch for millions of light years. Hubble observations reveal quasars where these magnetic jets collide with intergalactic gas, creating shockwaves that glow across the electromagnetic spectrum. Some beams punch holes through their host galaxies, while others trigger star formation in distant clouds like celestial dominoes. The quasar 3C273, for instance, sports a jet 90,000 light-years long, visible only because magnetic fields keep its particles coherent over cosmic distances. Without this magnetic focusing, the energy would dissipate into the void long before reaching such scales. Perhaps most astonishing is how quasars use magnetism to solve an astrophysical puzzle, the Eddington limit. This theoretical barrier dictates how fast a black hole can consume matter before radiation pressure stops further infall. Quasars routinely violate this limit by using magnetic fields to redirect excess energy into jets, essentially venting their overstocked furnaces sideways. It's why we see quasars from the early universe. These magnetic escape valves allowed them to feast voraciously while still shining brilliantly enough for us to detect 12 billion years later. Yet mysteries linger. Why do some quasars flicker unpredictably while others shine steadily? How do their magnetic fields remain stable across millions of years? Each new observation peels back another layer, revealing magnetism not just as a tool for destruction, but as the universe's ultimate power broker, turning the darkest objects into its brightest beacons. Far from being passive bystanders, these invisible forces write the rules for how the most extreme corners of the cosmos behave. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with enough force to outshine entire galaxies. But in those final, cataclysmic moments, something extraordinary happens to its magnetic field. As the star's core collapses inward at a quarter the speed of light, the dying star doesn't just destroy its magnetic legacy, it supercharges it, squeezing those invisible lines of force into a cosmic pressure cooker until they emerge a billion times stronger than before. Take the Crab Nebula, that glittering remnant from a supernova witnessed in 1054. What looks like a chaotic cloud of gas is actually a meticulously structured magnetic powerhouse. The collapsed core left behind a pulsar spinning 30 times per second acts like a dynamo, flooding the expanding debris with a magnetic field so intense it shapes every wisp and tendril. High-energy electrons spiral along these invisible threads at nearly light speed, creating the nebula's eerie blue glow in polarized light. Without this magnetic scaffolding, the crab would be just another formless dust cloud rather than the intricate cosmic tapestry we see today. The process begins in the star's final milliseconds. As the iron core implodes, protons and electrons get crushed together so violently they form a neutron star while amplifying the original magnetic field like a cosmic amplifier. When the rebounding shockwave blasts the star's outer layers into space, it carries these supercharged magnetic lines along for the ride. The result: a rapidly expanding shell where magnetism governs the debris like invisible puppet strings. In the Crab Nebula, these forces whip particles to such extreme energies that they emit synchrotron radiation, a brilliant light show caused by electrons spiraling around magnetic field lines like cars on a cosmic racetrack. Some supernova remnants take this magnetic mayhem even further. Cassiopeia A, the leftovers of a star that exploded around 1680, shows magnetic hotspots where field strength rival those near Magnetars. These localized zones act like cosmic accelerators, producing high-energy gamma rays detectable from Earth. Meanwhile, in the Vela supernova remnant, astronomers have found magnetic ropes, twisted bundles of field lines stretching light years across, possibly formed when the dying star's rotation got imprinted on its exploding envelope. What's truly remarkable is how these magnetized ghosts continue shaping their surroundings centuries after the explosion. The Crab's pulsar wind nebula, a dynamic bubble of particles and fields, keeps expanding at 1,500 kilometers per second, its magnetic fingers sculpting gas into delicate filaments. Some researchers believe these fields may even protect the nebula from dissipating too quickly, acting like an invisible cage that keeps the stellar debris coherent for millennia. Yet supernova remnants aren't just beautiful relics, they're cosmic recycling plants. Their magnetic fields help distribute heavy elements forged in the explosion, channeling iron, gold, and other metals into interstellar space where they'll eventually form new stars and planets. The very iron in your blood likely passed through such a magnetized maelstrom billions of years ago. These invisible forces don't just create stunning celestial artwork, they're the universe's way of ensuring nothing, not even a dying star's last breath, goes to waste. Cosmic rays streak across the universe at nearly the speed of light, carrying whispers of distant supernova and active galactic nuclei. But by the time these charged particles reach Earth, their origins have become a cosmic whodunit. The culprit, magnetic fields, those invisible highway robbers twisting and turning the paths of these subatomic messengers until their trajectories become nearly impossible to trace. Imagine throwing a handful of confetti into a tornado. That's essentially what happens when high-energy protons and atomic nuclei encounter the tangled magnetic webs stretching between galaxies. These particles don't travel in straight lines like light. Each proton or ion nucleus, some packing the energy of a well-thrown baseball despite being smaller than an atom, gets deflected by every magnetic field it encounters. A single cosmic ray emitted from a black hole jet millions of light years away might zigzag through hundreds of galactic magnetic domains before reaching us, its path so convoluted that pinpointing its source becomes like reconstructing a shredded letter blown across a city. Even the Milky Way's own magnetic field, relatively weak by cosmic standards, can bend an incoming ultra-high-energy cosmic ray by 30 degrees or more, completely masking its true origin. Scientists have developed ingenious ways to circumvent this celestial shell game. One approach tracks particles with such staggering energy above 10 to the 18th electron volts that they barely feel the Milky Way's magnetism. In 2017, the Pierre Auger Observatory traced a few of these ultra-rare particles back to a broad region near the active galaxy Centaurus A, marking the first tentative cosmic ray hotspot ever identified. Another method looks for secondary clues, like gamma rays or neutrinos produced when cosmic rays collide with interstellar gas which travels straight to us unaffected by magnetism. The deflection mystery has real consequences. Without knowing where cosmic rays come from, we can't fully understand how black holes and supernova distribute energy across the cosmos. Some theories suggest the most energetic particles might originate from galaxy clusters, where magnetic fields can act like enormous particle accelerators. Others point to void filaments, the vast threads of dark matter connecting galaxies, as potential highways for cosmic rays. Yet the same magnetic fields that hide cosmic ray origins also protect life on Earth. By scattering these particles, they prevent local concentrations that could bathe our planet in lethal radiation. It's a cosmic irony. The forces that erase the fingerprints of these intergalactic bullets also ensure they arrive as a gentle drizzle rather than a focused death ray. Every time a cosmic ray detector on Earth clicks, it's not just registering a particle, it's reading the final line of a story written in magnetic ink, with half the pages deliberately smudged. Between galaxies where space seems almost empty lies one of the universe's best-kept secrets, a whisper-thin web of magnetism stretching across millions of light-years. These intergalactic fields are so faint they'd struggle to nudge a single electron, yet their collective influence shapes the largest structures in existence. Unlike the concentrated fields around stars or black holes, this cosmic backdrop is more like a ghostly fingerprint left over from the universe's earliest moments, now amplified by eons of cosmic expansion. The origins of these fields remain hotly debated. One theory suggests they were born in the chaotic aftermath of the Big Bang, when quantum fluctuations imprinted tiny magnetic seeds onto the infant universe. Another points to the first generation of stars and galaxies, whose violent deaths in supernova and quasars could have flooded space with magnetized plasma. Whatever their source, these faint fields got stretched and woven into the cosmic web by the expansion of the universe, like invisible threads knit into the fabric of space-time itself. Detecting something so diffuse requires clever astrophysical detective work. Astronomers use the light from distant quasars as cosmic flashlights when their beams pass through magnetized regions. The polarization of the light subtly twists, betraying the presence of otherwise invisible fields. Other clues come from ultra-high-energy cosmic rays, whose paths bend slightly as they traverse these magnetized voids, scattering like compass needles in a hurricane. What's astonishing is how these sparse fields punch above their weight. In galaxy clusters where filaments of the cosmic web intersect, magnetic fields get concentrated enough to sculpt the behavior of superheated gas. The Perseus cluster, for instance, hosts magnetic bridges spanning hundreds of thousands of light-years, channeling plasma flows and preventing galaxies from evaporating into the void. Even in seemingly empty regions, these fields may guide the formation of primordial gas clouds, setting the stage for future galaxies. The real marvel lies in their persistence. Over billions of years, as galaxies collide and black holes erupt, these intergalactic fields endure, stretching but never breaking, like cosmic elastic. Some researchers speculate they could even store energy from ancient astrophysical cataclysms, acting as a fossil record of the universe's most violent events. Others suggest they might influence the growth of supermassive black holes by subtly steering intergalactic gas flows. Yet for all their quiet influence, these fields remind us that true emptiness doesn't exist in the cosmos. Even the darkest voids between galaxies hum with invisible forces, threads of magnetism woven into the universe's grand design since the dawn of time. They're the universe's oldest hidden infrastructure, fragile but unbreakable, silent but never still. Galaxy clusters, the universe's largest gravitationally bound structures, hold more than just hundreds of galaxies. They're also home to vast, invisible magnetic empires that shape their evolution in ways we're only beginning to understand. Take the Coma Cluster, a sprawling collection of over 1,000 galaxies located 320 million light-years away. Between its galaxies lies a thin, superheated gas known as the intracluster medium, and coursing through that gas are magnetic fields powerful enough to influence the fate of entire galactic neighborhoods. These fields don't just float idly in space, they actively heat the surrounding gas through a process called magnetic viscosity. As charged particles spiral along the twisted field lines, they collide with one another, transferring energy like bumper cars in a cosmic amusement park. Over time, this keeps the intracluster medium from cooling too quickly, preventing galaxies from forming stars at unsustainable rates. Without this magnetic regulation, galaxy clusters might exhaust their gas supplies prematurely, leaving behind stellar graveyards instead of vibrant galactic communities. But the real showstoppers are the relativistic particles these fields accelerate. In the Coma Cluster, astronomers have detected diffuse radio emissions stretching millions of light-years, telltale signs of electrons whipping through magnetic fields at nearly the speed of light. These particles gain energy not from traditional sources like supernova, but from the cluster's magnetic turbulence, which acts like a natural particle collider on a scale dwarfing anything we could build on Earth. X-ray observations reveal another twist. These fields sculpt the gas itself. Where magnetic pressure is strongest, it pushes against the intracluster medium, creating cavities and ripples visible in instruments like the Chandra X-ray Observatory. Some clusters even sport magnetized bubbles, vast regions where jets from supermassive black holes have inflated magnetic structures like cosmic balloons. The Perseus cluster showcases this perfectly, with its wispy gas filaments aligned along invisible magnetic threads like iron filings around a bar magnet. What makes these cluster-wide fields truly remarkable is their resilience, even when galaxies collide. An event that should shred orderly magnetic structures, the fields somehow reorganize, like a spider rebuilding its web after a storm. Some theorists suggest they're sustained by the constant churn of galaxy motions, while others propose they're relics from when clusters first formed, preserved for billions of years. Either way, they stand as proof that magnetism operates not just on stellar scales, but on the grandest stages the universe has to offer. Yet mysteries remain. How do these fields remain coherent across such vast distances? Why do some clusters show patchy, disorganized magnetism while others exhibit large-scale order? Each answer peels back another layer of how the invisible scaffolding of the cosmos shapes everything we see and much that we don't. The Sun's magnetic heartbeat pulses with remarkable regularity every 11 years. Its north and south poles flip places in a cosmic dance that shapes everything from solar storms to Earth's auroras. This rhythm isn't just a curiosity, it's etched across our star's face in a stunning pattern called the butterfly diagram, a celestial fingerprint revealing how sunspots migrate toward the equator like clockwork over each cycle. Named for its symmetrical, wing-like shape when charted over decades, this phenomenon connects the Sun's hidden magnetic machinations to the fiery eruptions we see on its surface. Sunspots, those dark blemishes marring the solar disk, are actually windows into the Sun's magnetic soul. Each one marks where tangled magnetic field lines pierce through the photosphere, inhibiting heat flow and creating cooler, darker regions. But they don't appear randomly. At the start of a new cycle, sunspots emerge at mid-latitudes around 30 degrees north and south. As the years pass, they creep steadily toward the equator, leaving behind a trail that, when mapped over time, forms the butterfly's characteristic wings. The diagram's elegance hides fierce complexity. It's the visible signature of a vast magnetic conveyor belt churning deep within the Sun, where plasma flows redistribute magnetic energy like a cosmic tapestry maker weaving invisible threads. The driving force behind this migration lies in the Sun's differential rotation. Its equator spins faster than its poles, dragging magnetic field lines like taffy until they snap and reorganize. This stretch and snap process, called the dynamo effect, fuels the 11-year polarity flip. When the cycle peaks, the sun's magnetic field becomes a tangled mess, unleashing solar maximum, a period of intense sunspot activity, flares, and coronal mass ejections. Then, as the butterfly's wings close near the equator, the field gradually simplifies until the poles reverse and the dance begins anew. Historical records reveal just how dependable this rhythm is. Astronomers have tracked sunspots since Galileo's time, but it wasn't until the mid-1800s that German amateur Heinrich Schwabe noticed their cyclical rise and fall. Later, British astronomer Edward Maunder mapped their latitudinal march, laying the groundwork for the butterfly diagram. Modern satellites like SOHO and SDO now capture this migration in exquisite detail, showing how magnetic flux tubes rise, twist, and eventually cancel out at the equator, a process that resets the sun's global field like a cosmic metronome. But the butterfly diagram isn't just a pretty pattern. It holds clues to solar anomalies like the Maunder minimum of the 1600s, when sunspots vanished for decades and Earth plunged into a little ice age. Similar slowdowns may explain why recent cycles have been unusually weak, sparking debates about whether the sun is entering another quiet phase. Some theorists even speculate that the butterfly's asymmetries, how one hemisphere often leads the other in magnetic activity, could hint at deeper instabilities in the solar dynamo. What makes this cycle truly universal is its reach. The solar wind carries the sun's flipped magnetism throughout the heliosphere, creating a ripple effect that touches every planet. When Voyager probes crossed into interstellar space, they detected the imprint of these polarity reversals in cosmic rays, proof that the sun's magnetic heartbeat echoes far beyond its visible light. From guiding space mission timing to influencing satellite operations, understanding the butterfly diagram isn't just about decoding the sun. It's about learning to navigate a solar system forever shaped by its rhythmic, invisible pulse. On September 1, 1859, British astronomer Richard Carrington witnessed something unprecedented through his telescope, a brilliant white flare erupting on the sun's surface. Little did he know that burst of light heralded an electromagnetic storm so powerful it would electrify telegraph wires, spark fires in newspaper offices, and paint the night sky with auroras so bright birds began singing as if dawn had arrived at midnight. The Carrington event remains the most intense solar storm ever recorded, a stark reminder of how the sun's magnetic tantrums can reach across 93 million miles to shake civilization itself. What unfolded over the next 18 hours was a cascade of celestial chaos. A coronal mass ejection, a billion-ton cloud of magnetized plasma raced toward Earth at over 4 million miles per hour, slamming into our planet's magnetic field with enough force to compress it by half. As the geomagnetic storm intensified, telegraph systems across Europe and North America failed spectacularly. Operators in Boston watched sparks leap from their equipment, igniting piles of paper. In Philadelphia, a telegraph clerk discovered he could send messages with batteries disconnected, powered solely by currents induced in the wires from the storm. Even in the pre-electric era, the world's rudimentary tech infrastructure proved staggeringly vulnerable. The true spectacle unfolded after sunset. Skies from Cuba to Hawaii blazed with crimson and emerald auroras normally confined to polar regions. Miners in the Rocky Mountains woke at midnight, convinced the glow was sunrise. Newspapers in Baltimore reported that the light was bright enough to read by, while gold prospectors in Australia mistook the phenomenon for a massive bushfire. The celestial light show wasn't just beautiful, it was the visible signature of solar particles spiraling down Earth's magnetic field lines, ionizing atmospheric gases at unprecedented latitudes. Modern simulations reveal just how close the Carrington storm came to catastrophe. Had the eruption occurred just 1 week earlier when the active sunspot cluster faced Earth more directly, the impact could have been twice as strong. Today, with our planet wired together by vulnerable power grids, satellites, and undersea cables, a repeat event could plunge continents into darkness for months. Transformers, the massive hard-to replace devices that step voltage up and down in power networks, would be particularly susceptible. In 2013, a study estimated that a Carrington-level storm could cost the U.S. economy alone up to $2.6 trillion in the first year, with full recovery taking up to a decade. The most chilling precedent comes from a near miss in July 2012. A solar eruption almost identical to the Carrington event tore through Earth's orbit, but our planet happened to be on the opposite side of the Sun at the time. NASA satellites later calculated the storm's intensity matched the 1859 event. Had it struck, we'd still be counting the losses. Yet the Carrington event wasn't just a disaster, it was a revelation. Scientists analyzing tree rings and ice cores found evidence of even more powerful storms in the distant past, suggesting our Sun is capable of magnetic outbursts far beyond what we've witnessed. Some researchers now classify these extreme solar eruptions alongside asteroid impacts and supervolcanoes as civilization-scale threats, natural hazards we're only beginning to take seriously. Space agencies have since launched early warning systems, while engineers work to harden power grids against electromagnetic surges. But perhaps the storm's greatest legacy is the humbling realization that our technological society, for all its sophistication, still dances to the tune of a star 93 million miles away, a star whose magnetic moods we're only beginning to understand. The search for habitable worlds beyond our solar system takes an unexpected turn when we consider magnetism, an invisible factor that could make or break a planet's chances of hosting life. While most exoplanet hunts focus on factors like distance from their star or atmospheric composition, astronomers are now developing ingenious ways to detect magnetic fields light years away, revealing which worlds might hold onto their atmospheres long enough for life to take root. One telltale sign comes from auroras. Just as Earth's magnetic field creates the northern lights by funneling solar particles toward the poles, exoplanets with robust magnetospheres might broadcast their presence through radio waves generated by similar interactions. In 2020, researchers picked up faint radio signals from an Earth-sized exoplanet orbiting the star GJ1151, hints of a possible magnetic field stirring 40 light-years away. These emissions, though a million times weaker than typical radio stations, suggest charged particles spiraling along magnetic field lines, offering tantalizing indirect evidence of a protective magnetic bubble. Another clue lies in how planets interact with their stars. Young, active stars frequently blast out flares and coronal mass ejections. A magnetic exoplanet would deflect these assaults, creating a bow shock, a visible compression zone where stellar wind slams into the planet's magnetic shield. The Hubble Space Telescope spotted this around the gas giant HD 209458b, where escaping hydrogen formed a comet-like tail shaped by an inferred magnetic field. Without such protection, atmospheres get stripped away over time, as Mars tragically demonstrated in our own solar system. But the holy grail of detection involves transit spectroscopy, analyzing starlight filtering through an exoplanet's atmosphere during orbit. A magnetic field leaves subtle fingerprints in how atmospheric particles distribute. Certain ions cluster near magnetic poles, while others spread along equatorial zones. In 2022, studies of the super-Earth Gliese 486b suggested uneven oxygen concentrations in its upper atmosphere, a pattern consistent with a global magnetic field channeling particles towards specific latitudes. The habitability implications are profound. A strong magnetic field does more than block radiation. It prevents atmospheric erosion, regulates climate by reducing atmospheric loss during stellar flares, and may even shield surface chemistry crucial for life's molecular building blocks. Planets orbiting red dwarfs, the most common stars in our galaxy, face particularly harsh stellar winds. Without magnetic armor, even worlds in the habitable zone could end up as barren as the Moon. That's why upcoming telescopes like the James Webb Space Telescope and the Square Kilometer Array Radio Observatory prioritize magnetic signatures in their hunt for Earth twins. Yet mysteries persist. Could tidally locked planets where one side permanently faces their star develop lopsided magnetic fields? Do ocean worlds with conductive saltwater layers generate aquatic dynamos? Each discovery peels back another layer of this cosmic puzzle, proving that in the search for life beyond Earth, magnetism isn't just an afterthought. It's the silent guardian that might determine whether distant worlds are wastelands or wonderlands. Moon rocks collected during the Apollo missions hold a shocking secret. Trapped within their crystalline structures is evidence that our cratered neighbor once boasted a magnetic field rivaling Earth's today. This discovery stunned scientists, as the Moon's core is barely 1% the volume of Earth, seemingly too small to sustain such planetary-scale magnetism. Yet analyses of these lunar samples reveal minerals magnetized in ways that only make sense if they cooled in the presence of a robust global field between 1 and 3.5 billion years ago, a revelation forcing us to rewrite lunar history. The mystery deepens when you consider how planetary magnetic fields form. Typically, they require three ingredients: a molten metallic core, rapid rotation, and vigorous convection, like Earth's churning outer core of liquid iron and nickel. The Moon, with its sluggish rotation and small size, shouldn't have maintained the internal heat needed to keep its core molten for long. One compelling theory suggests tidal forces from a much closer early Earth may have kept the Moon's interior simmering. Just as Jupiter's gravity stretches Io to create volcanic chaos, Earth's gravitational pull could have flexed the young Moon's core, generating enough friction to sustain both molten layers and convection currents essential for magnetism. Then there's the core crystallization hypothesis. As the Moon's initial magma ocean cooled, dense iron-rich minerals may have sunk toward the center while lighter elements rose, creating a dynamo effect similar to a lava lamp's motion. Computer simulations show this process could have jump-started a magnetic field for a few 100 million years, just long enough to imprint its signature on those ancient Apollo rocks. Some studies even propose that colossal impacts during the Moon's violent early history temporarily stirred its core like a cosmic spoon, giving brief boosts to magnetic activity. The implications reach far beyond lunar science. If such a small body could generate a strong field, similar processes might occur in icy moons like Europa or even large asteroids. It challenges our definition of what makes a world magnetically active and raises tantalizing questions about whether exomoons around distant gas giants could harbor protective fields, and by extension, conditions friendlier to life. Yet the Moon's magnetic past isn't just an academic puzzle. Those fossilized fields act as time capsules, preserving snapshots of the solar system's early chaos. By studying how lunar magnetism fluctuated before fading entirely around 1 billion years ago, we gain clues about Earth's own magnetic infancy, a period when both worlds may have sheltered each other under twin electromagnetic umbrellas against a far more hostile young sun. The Silent Rocks astronauts brought home half a century ago whisper secrets we're only now learning to hear, proving even the most familiar celestial bodies guard surprises that force us to rethink the cosmos. Venus presents a planetary paradox, a world nearly Earth's twin in size and composition, yet utterly desolate, with an atmosphere so thick it crushes landers within hours. The key difference: Venus lacks Earth's protective magnetic shield, leaving it exposed to the solar wind's relentless assault. Despite sharing a similar iron core and rocky makeup, something went catastrophically wrong in Venus's inner workings, turning it from a potential oasis into a scorching hellscape. The mystery starts with rotation, or the lack of it. Venus spins agonizingly slow, completing one day in 243 Earth days, longer than its year. This sluggish turn starves its core of the dynamo effect that powers Earth's magnetism. Without rapid rotation to churn molten metal, Venus's core may have cooled into a stagnant, layered mass, unable to generate the circulating currents needed for a global field. Recent simulations suggest an even grimmer possibility. Venus might have had an early magnetic field that catastrophically collapsed when its core crystallized, shutting off the dynamo like a blown fuse. Solar wind exploits this vulnerability mercilessly. ESA's Venus Express orbiter measured atmospheric loss rates 10 times higher than Earth's, with hydrogen and oxygen ions, water's building blocks being stripped into space. Unlike Earth, where our magnetosphere deflects most solar particles, Venus's upper atmosphere takes the full brunt. The impact tears molecules apart through a process called sputtering, creating an ion tail that stretches millions of miles behind the planet, visible in ultraviolet light like a cosmic scar. Over billions of years, this erosion likely removed enough water to cover Venus in a global ocean hundreds of feet deep. Yet Venus isn't completely defenseless. Its ionosphere, a charged upper atmospheric layer, interacts with solar wind to form an induced magnetosphere. This makeshift shield, generated by the Sun's magnetic field draping around the planet, creates weaker, localized protection. During solar maximum, when the Sun's activity peaks, this interaction actually thickens Venus's ionosphere, temporarily slowing atmospheric loss. It's a fragile balancing act, far less robust than Earth's intrinsic field, but enough to hint at how planetary magnetism isn't always all or nothing. The implications stretch beyond our solar system. As astronomers discover Earth-sized exoplanets, Venus stands as a cautionary tale, a reminder that size alone doesn't guarantee habitability. A planet could orbit in the Goldilocks zone with ample water, but without magnetic armor, its atmosphere might bleed away into the void. Some researchers speculate that Venus's fate could be common for planets orbiting calm M-dwarf stars where tidal locking stifles rotation. Others wonder if early Venus briefly enjoyed conditions ripe for life before its dynamo failed, turning paradise into a pressure cooker. What makes Venus's story particularly haunting is the chance it might have once mirrored Earth. Isotopic ratios in its atmosphere suggest it lost vast quantities of water, possibly as recently as 1 billion years ago. Magnetic field measurements from upcoming missions like NASA Veritas could reveal whether its core still harbors molten layers or if it's fully solidified, clues to how long its protective shield lasted, and whether its descent into Inferno was inevitable or a tragic fluke of celestial mechanics. For now, Venus remains a warning etched in acid clouds. In the cosmic drama of planetary evolution, magnetism isn't just a side feature. It's the difference between a living world and a lifeless wasteland. The Sun's influence doesn't stop at Pluto. It stretches far beyond, sculpting a colossal magnetic cocoon around our entire solar system. This teardrop-shaped force field, known as the heliosphere, extends over twice the distance to Pluto's orbit, with its tail trailing even farther into interstellar space like a comet's wake. Powered by the solar wind, a relentless stream of charged particles racing outward at 1,000,000 miles per hour, this bubble is our first line of defense against cosmic rays and other high-energy particles from deep space. Without it, these interstellar intruders would bombard planets at nearly light speed, irreversibly altering atmospheres and potentially sterilizing surfaces. What makes the heliosphere truly remarkable is how it's shaped by magnetic struggle. As the Sun hurtles through the galaxy, its outflowing solar wind collides with interstellar gas and dust, creating a turbulent boundary called the heliopause. Here, the Sun's magnetism wrestles with the Milky Way's own weak interstellar field, carving out a protective zone where the pressure of outgoing particles balances the inward push of galactic material. Voyager 1 crossed this frontier in 2012, measuring a sudden drop in solar particles and a spike in cosmic rays, humanity's first direct taste of interstellar space. But the heliosphere isn't just a passive shield, it's dynamic and ever-changing. During solar maximum, when the sun's activity peaks, intensified solar wind inflates the heliosphere like a balloon, pushing the boundaries outward. Conversely, in quieter periods, it contracts, allowing more cosmic rays to penetrate deeper into the inner solar system. These fluctuations leave chemical fingerprints in Earth's atmosphere and even influence cloud formation, suggesting our star's magnetic reach may subtly affect climate patterns over millennia. The heliosphere's structure holds surprises too. Instead of a smooth bubble, NASA's IBEX mission discovered strange ribbons of energetic particles tracing its outer edges, possibly where interstellar magnetic fields drape around the solar system like invisible fingers. Meanwhile, Cassini spacecraft data revealed the heliosphere might be more spherical than previously thought, its shape distorted by the local interstellar magnetic field like a rubber band stretching in the wind. Perhaps most astonishing is the heliosphere's role as a cosmic sieve. While it blocks most harmful galactic radiation, it curiously allows certain neutral atoms to slip through particles that become trapped in Earth's ice cores and lunar soil, recording the solar system's journey through different regions of the galaxy. By studying these interstellar stowaways, scientists have reconstructed our solar system's passage through a sparse interstellar cloud just 15 light-years wide. One will exit in another few thousand years. This magnetic bubble isn't unique to our Sun. Every star likely boasts its own version. But as the only heliosphere we can study up close, ours offers priceless insights into how planetary systems interact with the galaxy at large. From shielding primitive life on Earth to guiding future interstellar explorers, the Sun's invisible magnetic grasp remains one of the most underappreciated yet vital features of our cosmic neighborhood. Before planets take shape around a young star, their birth begins in a swirling disk of gas and dust where invisible magnetic threads act as cosmic architects. These protoplanetary disks, stretching hundreds of astronomical units across, aren't just passive clouds waiting to collapse. They're dynamic arenas where magnetism orchestrates the ballet of planet formation. Observations from radio telescopes like ALMA revealed dust grains aligning like compass needles along magnetic field lines, creating intricate patterns that defy simple gravitational explanations. At the heart of this process lies ionization, the same phenomenon that powers neon signs. Ultraviolet radiation from the newborn star strips electrons from gas molecules, creating a plasma soup where charged particles become enslaved to magnetic forces. This transforms the disk into a colossal electric generator, with differential rotation between inner and outer regions stretching magnetic field lines like taffy. The resulting tension creates turbulence that determines where dust grains can clump together and where they're ripped apart. Some simulations suggest these fields create dead zones, calm regions where planets can coalesce undisturbed, shielded from the violent churn of the surrounding disk. The influence doesn't stop at dust aggregation. Magnetic fields likely solve the mystery of how gas giants form fast enough to exist. Without magnetism, calculations show Jupiter-sized planets would take millions of years to accumulate their atmospheres, far longer than observed in young systems. But magnetized winds could funnel gas inward at accelerated rates, explaining how massive worlds emerge within mere thousands of years. These same fields may also launch spectacular bipolar jets, twin beams of particles shooting from the star's poles at hundreds of kilometers per second, their collimated structure betrayed by the tight grip of magnetic confinement. Perhaps most remarkably, these primordial fields might imprint themselves permanently on emerging worlds. Meteorites in our solar system contain minerals magnetized in ways that only make sense if the protoplanetary disk's field was present during their formation. Some astronomers speculate this could explain why certain asteroids show remnant magnetism despite lacking cores. They're fossilized relics of the disk's magnetic environment, frozen in time from the solar system's infancy. Modern telescopes are now mapping these fields directly through polarized light. When dust grains align magnetically, they scatter light with a distinct polarization signature. ALMA images of systems like HL Tauri show concentric rings where magnetism has organized material into planet-forming lanes, proving these invisible forces don't just accompany planet birth, they actively shape it. The implications stretch beyond our cosmic neighborhood. If magnetic fields are universal features of protoplanetary disks, they could explain why exoplanetary systems show such diverse architectures. From hot Jupiters hugging their stars to distant ice giants, the hand of magnetism may have guided them all to their present orbits, leaving its imprint on every world that forms under its invisible sway. Among the galaxy's stellar oddities, HD 45166 stands out as a cosmic enigma, a rare Wolf-Rayet star wrapped in a magnetic vise so intense it bends its own stellar winds into a luminous, sculpted halo. Unlike typical stars where magnetism plays a subtle role, this celestial rebel boasts a field 100,000 times stronger than the Sun's, turning its violent outflows into a mesmerizing cosmic light show. Wolf-Rayet stars are already stellar outliers, massive, evolved giants shedding their outer layers in fierce winds that blast material into space at millions of miles per hour. But HD 45166 takes this chaos and imposes order. Its magnetic grip is so powerful that instead of expanding uniformly, the star's ejected gas gets funneled along magnetic field lines, forming a glowing, structured nebula that resembles intricate lacework in telescopic images. This isn't just stellar wind, it's stellar wind on a leash, forced into patterns that reveal the invisible architecture of the star's magnetic prison. What makes this star truly bizarre is its origin story. Most massive stars with strong magnetic fields are young, their magnetism inherited from the turbulent clouds that birthed them. HD 45166 defies expectations. It's in a late stage of stellar evolution, having already burned through its hydrogen and now fusing heavier elements in its core. One theory suggests it might be the product of a stellar merger, where two stars collided and their combined magnetic fields amplified into something monstrous. Another possibility is that its core underwent a catastrophic rearrangement, suddenly concentrating magnetic flux like a cosmic lightning bolt frozen in time. The consequences are visible light years away. The star's magnetized halo glows in polarized light, a telltale sign of electrons spiraling along magnetic field lines. Spectroscopic observations reveal elements like helium and carbon being flung outward in precise jets, their paths dictated by the star's relentless magnetic grip. In most stars, these elements would diffuse into space as an even haze. Here, they're channeled like water through a cosmic sprinkler system, painting intricate patterns across the interstellar canvas. Yet HD 45166's most tantalizing secret might be its fate. Wolf-Rayet stars often end their lives as supernova or gamma-ray bursts. With magnetism this extreme, its death throes could produce a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth. Some researchers speculate that the star's final explosion might even unleash a magnetar-powered supernova, a rare event that could temporarily outshine its entire host galaxy. Until then, this magnetic maverick continues to challenge our understanding of how stars live, die, and sculpt the universe with forces unseen. White dwarfs, the dense, Earth-sized cores left behind after stars like our Sun exhaust their nuclear fuel, often hide astonishing magnetic secrets beneath their unassuming glow. Take Sirius B, the faint companion to the brightest star in our night sky. At first glance, it appears as just another cooling ember in the cosmos, but spectroscopic observations reveal a startling truth. Its light is split into multiple wavelengths by a magnetic field millions of times stronger than Earth's, warping the very fabric of the atoms in its atmosphere. This phenomenon, called Zeeman splitting, occurs when intense magnetism alters electron energy levels, causing spectral lines to divide like branches of a tree, a telltale signature of magnetic power lurking within. What makes these magnetic white dwarfs so puzzling is their origin. Unlike neutron stars, where crushing gravity amplifies magnetic fields during collapse, white dwarfs form through relatively gentle stellar shedding. One leading theory suggests their magnetism might be fossilized traces of the star's original field, concentrated as the outer layers blew away. Imagine squeezing a bar magnet into a sphere the size of Earth. The field strength would skyrocket simply from the compression. Alternatively, some white dwarfs might gain their magnetism through mergers, when two stars collide and their combined magnetic fields twist into something far more potent. The case of Re J0318-296, a white dwarf with a field so strong it polarizes light like a cosmic prism, supports this idea. Its extreme magnetism aligns with simulations of stellar collisions. The implications stretch far beyond stellar oddities. By studying how these fields distort spectral lines, astronomers gain a unique window into white dwarf interiors. Magnetic white dwarfs often show uneven surface fields, with patches of intense magnetism resembling cosmic bruises, evidence of hidden dynamos or crystallized layers beneath their surfaces. Some, like GRW plus 70°8247, even exhibit magnetic spots that rotate in and out of view, offering clues about how these dying stars redistribute internal material as they cool over billions of years. Perhaps most intriguing is what these objects reveal about stellar afterlife. Magnetic white dwarfs account for roughly 20% of all known white dwarfs, suggesting strong fields might be a common phase in stellar evolution rather than a rarity. Their influence could explain anomalous observations in supernova remnants or even shed light on how planets orbiting them. Yes, some white dwarfs host surviving worlds experience radically different environments than those around non-magnetic counterparts. As we discover more of these magnetic ghosts, they challenge our assumptions about how stars live, die, and leave behind invisible fingerprints that endure long after their light fades. Ganymede, Jupiter's largest moon, holds a cosmic distinction. It's the only moon in our solar system known to generate its own magnetic field, creating a miniature magnetosphere nested within Jupiter's colossal magnetic embrace. This layered magnetic dance produces spectacular auroras that glow where the two fields intersect, a celestial light show powered by competing invisible forces. Unlike Earth's northern lights, which stem from solar particles hitting our atmosphere, Ganymede's auroras arise from electrons accelerated along the complex boundary where its intrinsic field clashes with Jupiter's. The Hubble Space Telescope has captured these faint ultraviolet rings, revealing how the moon's magnetic bubble stubbornly resists its planet's overwhelming influence, carving out a protective cavity in Jupiter's plasma-filled environment. Just one Jovian moon away, Io presents a stark contrast, a volcanic hellscape where Jupiter's magnetism turns geological chaos into an electrical powerhouse. Lacking its own magnetic field, Io instead becomes a conductive cog in Jupiter's machinations. As the moon plows through Jupiter's magnetosphere at 46,000 miles per hour, it generates a staggering 3 million amps of current along invisible magnetic flux tubes connecting it to Jupiter's poles. This cosmic circuit fuels the most powerful auroras in the solar system, with each of Io's footprints in Jupiter's atmosphere radiating several terawatts brighter than Earth's entire global power consumption. The tidal forces behind Io's famous volcanoes owe their intensity to this magnetic relationship. Jupiter's gravity stretches Io, but the moon's conductive interior, heated by those looping currents, enhances the tidal flexing, turning its mantle into a simmering pressure cooker. Sulfur-rich plumes erupting hundreds of miles high become ionized by Jupiter's radiation, seeding a donut-shaped plasma torus along Io's orbit that beams radio waves detectable from Earth. When volcanic activity spikes, this torus brightens like a neon sign, offering astronomers a remote monitor for eruptions on the distant moon. Even stranger magnetic interactions unfold at Europa, where Jupiter's field may indirectly safeguard its subsurface ocean. As the moon orbits, Jupiter's rotating magnetosphere induces electric currents in Europa's salty underground sea, generating secondary magnetic fields detected by the Galileo spacecraft. These readings provide crucial evidence for the ocean's existence and salinity, while hinting at electromagnetic heating that could sustain hydrothermal vents, potential oases for extraterrestrial life. The takeaway is profound. Moons aren't just passive rocks orbiting giants, they're dynamic players in electromagnetic symphonies. From Ganymede's defiant magnetic bubble to Eo's high-wire electrical act, these interactions transform simple orbital mechanics into theaters of invisible forces with visible consequences. As we search for life beyond Earth, understanding how moons and planets magnetically collaborate or catastrophically clash could redefine what we consider a habitable world. Beyond the orbit of Neptune, where sunlight dwindles to a faint twilight, the Kuiper belt holds frozen relics from our solar system's infancy, and some may carry magnetic whispers from that ancient era locked within their icy cores. These distant worlds, untouched by the warmth of the sun for billions of years, could preserve primordial magnetic fields like cosmic time capsules, offering clues to the chaotic conditions that shaped our planetary neighborhood. Consider Pluto's moon, Charon. When New Horizons flew past in 2015, it detected surprising geological activity on this supposedly dead world, canyons stretching hundreds of miles and hints of past cryovolcanoes. Such features typically require internal heat, which small bodies shouldn't retain after eons in the deep freeze. One provocative explanation: remnant magnetism from their formation, trapped in subsurface oceans or mineral deposits. If even a fraction of the solar nebula's original magnetic field got frozen into these objects during their birth, it could have influenced their chemistry and structure in ways we're only beginning to imagine. The most tantalizing evidence comes from iron meteorites found on Earth, some bearing magnetic imprints stronger than Earth's current field. These space rocks likely originated in the asteroid belt, but their bigger Kuiper belt cousins might harbor even more dramatic records. Imagine a world like Haumea, the football-shaped dwarf planet spinning rapidly with crystalline water ice coating its surface. Simulations suggest such rapid rotation could have amplified any initial magnetism during formation, creating fields intense enough to organize nearby dust into unusual patterns, structures we might spot if future probes could measure their subtle influence on passing solar wind. Detecting these weak signals poses monumental challenges. The traditional magnetometers used at Mars or Jupiter would struggle with the Kuiper belt's extreme distances and faint fields. But innovative techniques could bridge the gap. Some scientists propose analyzing how charged particles from the solar wind scatter around objects like Makemake. Anomalies in these interactions might betray hidden magnetism. Others suggest studying surface colors. Magnetically active worlds could have darker patches where solar particles get funneled along magnetic lines, chemically weathering specific regions like cosmic rust stains. The implications stretch far beyond curiosity. If Kuiper belt objects do preserve ancient fields, they'd provide a missing link in understanding how planetary magnetism evolves over billions of years. Did Neptune's migration scramble original magnetic alignments? How did the Sun's early magnetic outbursts affect these frozen outposts? Each answer could rewrite chapters of our solar system's history and hint at how magnetism shapes icy worlds orbiting distant stars. Until we send new missions to this twilight realm, these magnetic mysteries will linger like ghosts in the outer dark, waiting to share secrets from a time when the planets were just taking shape. Deep within the frigid vastness of interstellar space, molecular clouds drift like cosmic wombs, dark, dense, and crackling with invisible magnetic energy. These colossal structures, spanning light years and containing enough material to form thousands of stars, might seem like passive repositories of gas and dust. But hidden beneath their serene appearance, a silent battle rages between gravity's relentless pull and magnetism's stubborn resistance. Without this magnetic tug-of-war, stars would form in chaotic bursts, and planetary systems might never achieve the delicate architectures that allow worlds like ours to exist. The physics at play here is deceptively simple yet profoundly consequential. As gravity compresses these clouds, their magnetic fields frozen into the ionized gas push back like cosmic springs. Charged particles spiral along field lines, creating an invisible scaffold that slows collapse to a crawl. Imagine trying to pour molasses through a sieve made of rubber bands. That's essentially how magnetism throttles star formation. In the Orion Molecular Cloud Complex, astronomers have observed this process firsthand, with dust grains aligning like compass needles along magnetic filaments, betraying the presence of forces strong enough to reshape an entire stellar nursery. What's truly remarkable is how these fields dictate the birth of solar systems. As pockets of gas eventually overcome magnetic resistance and contract, the field lines don't just vanish, they get dragged inward, twisted into helical coils that rotate with the infant star. This spinning magnetic architecture becomes the blueprint for planets, funneling material into a disk where worlds will later assemble. The Hubble Space Telescope has captured protoplanetary disks with magnetic braids so intricate they resemble fingerprints, unique signatures of the invisible forces that shape them. Some theories suggest Jupiter's bizarre, lopsided magnetic field might even be a fossilized relic of these early disk dynamics preserved for billions of years. The implications extend beyond our cosmic neighborhood. Observations of distant molecular clouds reveal magnetic strengths varying wildly, some barely resisting gravity, others strong enough to halt collapse entirely. This cosmic diversity might explain why galaxies like the Milky Way produce stars at a steady trickle, while starburst galaxies churn them out frenetically. In the Tarantula Nebula, where magnetic fields are unusually weak, stars form in violent fireworks displays. Contrast that with the quiet magnetism of the Taurus molecular cloud, where gentle fields nurture slower, more orderly stellar births. Yet mysteries linger. How do these fields initially form? Some point to turbulent gas flows in the interstellar medium, while others invoke primordial magnetism dating back to the Big Bang. And when fields finally succumb to gravity's pull, their energy doesn't just disappear, it gets converted into heat, radiation, and even kinetic energy that can launch protostellar jets. These high-speed outflows, seen erupting from young stars like Herbig-Haro objects, are essentially magnetism's last stand, a final release of pent-up energy before a new solar system takes shape. Perhaps most poetically, these molecular clouds remind us that creation in the cosmos is never a free-for-all. The same forces that prevent chaotic collapse also ensure stability, a delicate balance that allowed our Sun and its planets to form at just the right pace, in just the right conditions. Next time you gaze at the night sky, remember, the stars above might owe their very existence to the invisible magnetic threads woven through the darkness, patiently guiding chaos into order. Rising like colossal hourglasses from the Milky Way's core, the Fermi bubbles stretch 25,000 light-years above and below our galactic plane. Twin towers of searing gamma rays that glow with the aftermath of an ancient cataclysm. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these structures aren't just remnants of some forgotten explosion. They're a cosmic crime scene where magnetism may have played the leading role in shaping one of the most enigmatic features in our galaxy. What makes these bubbles truly extraordinary is their intricate magnetic scaffolding. Polarized radio emissions reveal vast, organized field lines threading through the bubbles like the grain in a piece of cosmic wood, evidence that whatever launched these structures did so with enough force to align magnetism on an unimaginable scale. Some theories point to Sagittarius A, our galaxy's supermassive black hole, which may have experienced a violent feeding frenzy millions of years ago. As it devoured stars or gas clouds, the resulting energy could have blasted magnetized plasma outward along its poles, inflating these bubbles like cosmic balloons. But there's a twist: these fields aren't just passive leftovers. They're actively accelerating particles to near light speeds even today. The bubble's edges shimmer with synchrotron radiation, the telltale glow of electrons spiraling around magnetic field lines. This suggests the original outburst didn't just create static structures. It established an ongoing particle accelerator that continues to shape high-energy physics across a region spanning half the visible sky. Alternative explanations add layers to the mystery. Could these bubbles be the cumulative effect of hundreds of supernovae erupting in the galactic center, or perhaps evidence of dark matter annihilations where theoretical particles collided and unleashed pent-up energy? The bubble's sharp edges argue against a slow buildup. They look more like the result of a sudden titanic release, frozen in time as they expanded into the galactic halo. One thing's certain: the Fermi bubbles are rewriting our understanding of galactic ecology. Their magnetic frameworks act like cosmic dams, preventing the escape of high-energy particles that might otherwise flood the galactic disk. Some researchers speculate these fields could even influence how gas falls back into the Milky Way, seeding future star formation in a self-regulating cycle we're only beginning to comprehend. The most tantalizing clue lies in their symmetry. Perfectly balanced above and below the galaxy, these structures hint at an eruption so precisely channeled that it could only have been guided by something as disciplined as a black hole's magnetic funnel, or as exotic as a dark matter heartbeat. Whatever their origin, the Fermi bubbles stand as a humbling reminder that even our home galaxy harbors violent secrets, their invisible magnetic skeletons still buzzing with energy from an event that may have reshaped the Milky Way long before humans walked the Earth. At the solar system's outer frontier, where the sun's influence wanes and interstellar space begins, Voyager 1 encountered something extraordinary, a turbulent zone scientists dubbed the Magnetic Highway. This bizarre region, located about 11 billion miles from Earth, marks where the sun's magnetic field lines abruptly reorganize, connecting with the magnetic fabric of the galaxy itself. Instead of the orderly spiral pattern seen closer to the sun, here the field lines fold back on themselves like cosmic spaghetti, creating a chaotic network where solar particles can escape outward while interstellar particles stream inward. The discovery came in 2012 when Voyager's instruments detected a sudden 100-fold increase in cosmic rays from deep space, alongside a corresponding drop in solar particles. At the same time, the probe's magnetometer recorded magnetic fields shifting direction like a weather vane in a hurricane. This wasn't the calm boundary researchers expected. It was a dynamic interchange where the sun's magnetic dominance gives way to the Milky Way's influence. Imagine two vast oceans meeting, their currents intertwining in a froth of charged particles and twisted field lines. What makes this highway so unique is its role as a particle accelerator. Solar wind ions, no longer constrained by the sun's magnetic grip, get flung outward along these reconnected field lines, gaining enough energy to escape entirely. Meanwhile, high-energy cosmic rays from supernova and other galactic sources ride the inbound lanes, penetrating deeper into the solar system than previously possible. Voyager's data revealed these particles don't just drift passively, they surf along the magnetic contours, creating a buzzing interchange of matter and energy. Scientists now believe this region acts as a pressure release valve for the heliosphere. Without it, the buildup of solar particles at the edge of our system might distort the entire protective bubble. The magnetic highway's tangled geometry allows for a smoother transition, like an airlock gradually equalizing pressure between two environments. Recent models suggest similar structures might exist around other stars, hinting at a universal mechanism for how stellar systems interact with their galactic surroundings. Yet mysteries linger. Voyager observed the highway's magnetic turbulence fluctuating unpredictably, with particles appearing and vanishing in ways that defy simple explanations. Some theorists speculate this could be evidence of magnetic reconnection events, invisible short circuits, where field lines snap and realign, releasing bursts of energy. Others propose the chaos stems from interstellar magnetic fields pressing against the heliosphere like invisible fingers, warping the boundary into unpredictable shapes. As Voyager continues its journey into true interstellar space, the magnetic highway stands as one of its most profound discoveries, a reminder that even at the solar system's edge, invisible forces continue to shape our cosmic neighborhood in ways we're only beginning to decipher. Far from being a static border, this dynamic frontier pulses with energy, a testament to magnetism's far-reaching influence across the vast expanses of space. Neutron stars may appear perfectly smooth from a distance, but their surfaces hide a violent secret: crusts of iron nuclei so dense they form a crystalline lattice stronger than steel, yet brittle enough to shatter under the unimaginable strain of their own magnetic fields. These cosmic earthquakes, known as starquakes, unleash bursts of X-rays visible across the galaxy and can abruptly alter a neutron star's spin like a figure skater extending their arms mid-twirl. The crust of a neutron star is no ordinary material. Imagine compressing Mount Everest into a teaspoon. That's the density we're dealing with, where atoms get crushed into a quantum-degenerate soup. The surface solidifies into a rigid shell just a kilometer thick, floating atop a superfluid core. But this crust isn't static. It's under constant siege from magnetic fields trillions of times stronger than Earth's, which gradually warp and twist it like taffy. When the tension becomes too much, the crust fractures in milliseconds, releasing pent-up energy equivalent to 1,000 solar flares. NASA's NICER telescope has captured these events in stunning detail, watching as X-ray pulses spike during crustal ruptures, then fade like cosmic aftershocks. What makes these starquakes truly bizarre is how they mess with the star's rotation. Before a quake, the crust and core spin in sync, bound by magnetic forces. But when the crust cracks, it momentarily decouples like a spinning egg whose shell slips against the liquid inside. The result, sudden spin changes called glitches, where the star's rotation speed can jump by 1 part in a million. The Vela pulsar famously glitches every few years, its crust shivering as magnetic stresses reset its internal dynamics. These events aren't just curiosities, they're rare windows into neutron star interiors, revealing how superfluid vortices in the core interact with the crust's lattice. The aftermath of a starquake looks nothing like earthquakes on Earth. Instead of tectonic plates shifting, neutron star crusts undergo quantum rearrangements, nuclei popping into new configurations like a Rubik's Cube snapping into place. Some theories suggest these fractures might even trigger magnetic field reconfigurations, explaining why young magnetars suddenly become quieter after major X-ray outbursts. It's as if the star's entire magnetic skeleton gets a reset, with freshly broken crustal plates settling into less strained positions, yet some puzzles remain. Why do certain neutron stars glitch while others don't? How deep do these fractures penetrate? Recent observations of the Crab pulsar show its glitches precede X-ray flares, suggesting the quakes might begin deep beneath the surface before propagating outward. Each detection peels back another layer of mystery, proving that even the densest objects in the universe aren't immune to the cracks and groans of cosmic aging, a reminder that magnetism's grip can shatter even the strongest materials nature can forge. Deep in the cosmic zoo of neutron stars, one oddball stands out by breaking all the rules: SGR 0418, the celestial equivalent of a quiet introvert at a heavy metal concert. While its magnetar cousins boast magnetic fields powerful enough to rearrange your molecules from 1,000 miles away, this enigmatic object barely manages a field 1,000 times weaker, barely noticeable by neutron star standards. Discovered in 2009 through its sporadic X-ray bursts, SGR-0418 initially seemed like just another magnetar, until measurements revealed its shockingly modest magnetism, throwing decades of theories into disarray. The puzzle lies in how magnetars supposedly form. Conventional wisdom says these ultramagnetic neutron stars amplify their fields during birth. When a massive star collapses, its original magnetic field gets compressed into a city-sized package, intensifying to absurd levels. But SGR-0418's field strength barely exceeds that of an ordinary pulsar, despite displaying classic magnetar behaviors like sudden energy releases and slow spin-down rates. It's as if a sprinter won Olympic gold while jogging. The performance doesn't match the equipment. One radical explanation suggests SGR-0418 might be a magnetar in disguise, its true field hidden beneath the surface. Like an iceberg with most of its mass underwater, this star could harbor intense internal magnetism that only occasionally pierces through its crust. Supporting this idea are observations of rare, brief flares where its X-ray emissions spike as if trapped magnetic energy briefly escapes. Another theory proposes it's a magnetar past its prime, a once powerful object whose field has decayed over millennia, offering a preview of what our galaxy's mighty magnetars might become given enough time. The most tantalizing possibility, SGR-0418 represents an entirely new class of neutron star, one where magnetism isn't the dominant force shaping its behavior. Some researchers speculate thermal energy trapped in its superdense crust could drive its outbursts instead, challenging the assumption that all magnetar activity requires extreme magnetic fields. If true, it would mean our current magnetar catalog might include imposters, their X-ray fireworks powered by different physics entirely. What makes this cosmic rebel especially valuable is what it reveals about magnetic field decay. By studying how SGR-0418's weak field still manages to produce magnetar-like bursts, scientists gain clues about how quickly neutron star magnetism fades, a key factor in understanding stellar life cycles. Its very existence proves the universe still has surprises up its sleeve, reminding us that even the most established cosmic categories have exceptions waiting to rewrite the rules. Behind Earth's protective magnetic shield lies a cosmic battleground where invisible forces clash in spectacular fashion, the magnetotail. Stretching hundreds of thousands of miles into space opposite the Sun, this elongated shadow of our planet's magnetism isn't just an inert wake. It's a dynamic zone where energy builds, snaps, and explosively releases through a process that lights up our polar skies. Every few hours, under the right conditions, stretched magnetic field lines here undergo a dramatic transformation, reconnection, where oppositely oriented lines violently break and relink, catapulting plasma toward Earth at breathtaking speeds. The mechanics resemble a cosmic rubber band snapping. Solar wind drags Earth's magnetic field lines sunward on the day side, but as they flow over the poles and converge on the night side, they stretch into a long tail under relentless tension. Eventually, the stressed field lines near the center of the tail can't hold. They rupture and reconfigure into new loops, some snapping back toward Earth while others blast downwind into space. The energy released in these events rivals thousands of nuclear explosions, accelerating electrons and protons to nearly light speed. NASA, a magnetospheric multiscale mission, has flown through these reconnection sites, capturing data showing how electrons get ejected like cosmic pinballs during the process, their paths spiraling chaotically as they're caught in the magnetic chaos. These explosive reconnections don't just vanish into the void. They trigger dazzling consequences closer to home. when the accelerated particles race down the newly reconnected field lines toward Earth's poles, they smash into oxygen and nitrogen atoms in the upper atmosphere, igniting shimmering auroras. But the effects go beyond pretty lights. The sudden injection of energy disturbs Earth's entire magnetic envelope, creating geomagnetic substorms, brief but intense disturbances that can induce currents in power grids, disrupt radio communications, and even threaten satellites with surges of radiation. The Great Blackout of 1989, which left 6 million people without electricity across Quebec, traces its origins to one such substorm over North America. What's truly fascinating is how these events follow a predictable pattern. First, the tail's magnetic pressure builds as solar wind energy accumulates, like winding up a jack in the box. Then, within minutes, reconnection initiates near Earth, around 100,000 miles downstream. Plasma jets shoot both planetward and tailward at over 1 million miles per hour, while the auroral oval, a ring of light around the poles, brightens and expands. Finally, the system stabilizes, only to begin the cycle anew. Satellites like Themis have mapped this sequence in exquisite detail, revealing how energy cascades through the magnetosphere like dominoes falling in precise order. Yet mysteries linger. Why do some reconnection events trigger full-blown substorms while others fizzle? How do the microscopic physics of electron motion scale up to planet-sized phenomena? Recent discoveries of depolarization fronts, abrupt shifts in the tail's magnetic geometry, suggest hidden layers of complexity in how energy transports toward Earth. Some theories even propose that multiple reconnection sites can interact like scattered wildfires, their combined effects amplifying the overall disturbance. The Magnetotail's reconnection drama proves that Earth's magnetic field is far from a static shield. It's a living, breathing entity, constantly storing and releasing energy in a cycle that connects the solar wind's fury to the glow of our northern lights. Each snap of those magnetic lines reminds us that even in the vacuum of space, nothing ever stays still. Energy always finds a way to transform, often in the most visually stunning ways imaginable. Somewhere in the sun's seething atmosphere, an invisible frontier marks where the solar wind transforms from a gentle breeze into a supersonic torrent, the Alfvén critical point. This elusive boundary, named after Nobel laureate Hans Alfvén, represents the moment magnetic forces lose their grip on the sun's plasma, unleashing particles to race outward at speeds exceeding 1 million miles per hour. It's here, roughly 10 to 20 solar radii above the surface, that the sun's corona transitions from a magnetically dominated cage to the free-flowing solar wind we encounter throughout the solar system. The physics at this threshold are deceptively simple yet profoundly consequential. Below the Alfvén point, the sun's magnetic field lines act like taut rubber bands, channeling and restraining charged particles. Plasma here moves in sync with these magnetic contours, trapped in a complex dance where energy transfers between particles and fields in a continuous feedback loop. But as the corona expands outward, the magnetic field weakens with distance until, like a puppet cutting its strings, the solar wind breaks free, its kinetic energy finally overwhelming magnetic tension. NASA Parker Solar Probe, which pierced this boundary in 2021, measured the shift in stark terms, sudden drops in magnetic fluctuations paired with a surge in particle velocity, as if the plasma had crossed an invisible finish line. What makes this transition so pivotal is how it solves one of the sun's longest-standing mysteries: why the corona, despite being farther from the solar core, blazes at millions of degrees while the surface simmers at mere thousands. The Alfvén point acts as a cosmic energy valve, where magnetic waves generated by turbulent convection below crash and release their pent-up heat like ocean waves breaking on a shore. These Alfvén waves, first theorized in 1942, carry energy upward until they dissipate near this critical zone, superheating the corona in the process. Instruments aboard the Solar Orbiter spacecraft have captured these waves in action, revealing how their interactions create nanoflares, countless tiny explosions that collectively bake the corona to unimaginable temperatures. The boundary's location isn't fixed. It pulses and shifts with the Sun's 11-year activity cycle. During solar maximum, heightened magnetic activity pushes the Elfvane point farther outward, while at quieter periods it contracts closer to the surface. This dynamism affects everything from solar wind density to the frequency of geomagnetic storms at Earth. Historical data suggests the point might have lingered unusually close to the Sun during the 17th century Maunder minimum, potentially explaining the period's eerily calm space weather and its correlation with Earth's Little Ice Age. Recent discoveries add even more intrigue. Some plasma streams appear to stall near the Elfvane point, creating turbulent eddies where particles get briefly trapped before escaping. These delay zones might explain why certain solar wind bursts arrive at Earth with unexpected timing, complicating space weather forecasts. Other observations hint at magnetic reconnection events occurring just below the boundary, sudden rearrangements of field lines that inject extra energy into escaping plasma, like a slingshot giving one final boost to its projectile. Understanding this frontier isn't just academic, it's key to predicting solar storms that threaten satellites and power grids. The Elfvane point's behavior influences how coronal mass ejections accelerate, determining whether they'll deliver a glancing blow or a direct hit to Earth. Simulations now suggest that future missions might even manipulate this region artificially using targeted magnetic pulses to nudge storm trajectories away from our planet. From shaping the solar wind's fundamental properties to guarding our technological civilization, this unseen boundary proves that some of the Sun's most profound mysteries hide not in its fiery depths, but in the ghostly transition where magnetism yields to the void. High above our planet, where Earth's magnetic shield traps swarms of charged particles, an astonishing pattern emerges: delicate stripes of electrons painting orderly bands across the chaos of the radiation belts. These zebra stripes, first spotted by NASA Van Allen probes in 2014, shouldn't exist according to classical physics. In the frenetic, high-energy environment of the Van Allen belts, particles should scatter randomly like billiard balls in a cosmic pool hall. Yet there they are, neat, repetitive bands where electron densities rise and fall with eerie precision, as if an invisible comb had raked through the radiation. The secret lies in Earth's rotation and a subtle quirk of geomagnetic asymmetry. Our planet's magnetic field isn't perfectly aligned with its rotational axis. It tilts about 11 degrees, creating a slight wobble as Earth spins. This minor imperfection has outsized consequences for trapped electrons. Each rotation drags the magnetic field along, generating weak electric fields that nudge particles into synchronized waves. Think of it like pushing a child on a swing. Tiny, timed pulses can build into large, resonant motions. Over days to weeks, electrons responding to these gentle pushes organize themselves into alternating zones of high and low density, forming stripes spaced roughly 15 degrees apart in magnetic longitude. What makes these stripes so baffling is their resilience. Solar storms and geomagnetic disturbances that violently shake the radiation belt somehow leave the zebra pattern intact. Even when intense space weather scrambles particle distributions elsewhere, the stripes reappear like a ghostly echo, reforming within days. Observations suggest they're not just surface features, they penetrate deep into the belt structure, revealing hidden order beneath the apparent chaos. The stripes even fluctuate with Earth seasons, growing more pronounced during equinoxes when the solar wind aligns optimally with our planet's magnetic tilt. Scientists now suspect these patterns might be universal. Similar striping could exist around magnetized exoplanets or even in the radiation environments of gas giants. Jupiter's colossal magnetic field, for instance, might host analogous structures woven into its deadly radiation belts. Closer to home, understanding zebra stripes could revolutionize how we protect satellites. their predictable structure might offer safe lanes where spacecraft could avoid the belt's harshest radiation. Yet mysteries linger. Why do protons in the belts, despite being similarly charged, not form matching stripes? How do the patterns maintain coherence across thousands of miles? Each unanswered question peels back another layer of our planet's intricate magnetic personality, proving that even in the most hostile reaches of near-Earth space, nature finds ways to impose order. The Van Allen belts, long considered a chaotic no-man's land, now reveal themselves as a cosmic canvas where Earth's quiet rotation paints stripes across the void. The Moon's surface hides a series of ghostly patterns, delicate, bright swirls stretching for miles across the gray lunar plains like cosmic brushstrokes. These mysterious formations, known as lunar swirls, glow conspicuously against the darker regolith, their origin puzzling scientists for decades. What makes them even more intriguing is their uncanny alignment with patches of localized magnetism, areas where the Moon's crust holds remnants of ancient magnetic fields. Unlike Earth's global shield, these lunar magnetic pockets are small but mighty, creating invisible umbrellas that may deflect the relentless solar wind and sculpt the landscape in unexpected ways. High-resolution images from NAS, a lunar reconnaissance orbiter, reveal swirls like Rayner Gamma, a sprawling serpentine pattern near the Moon's western edge. The swirl's bright tendrils seem almost painted onto the surface, untouched by the darkening effects of space weathering that normally blanket lunar terrain. One leading theory suggests these patterns emerge because magnetic bubbles embedded in the crust act like miniature force fields, bending the path of solar wind particles away from certain areas. Over millennia, the unprotected regions darken as solar wind implants hydrogen and other elements into the soil, while the shielded zones remain pristine and reflective, creating the swirling contrast we see today. But how did these magnetic anomalies form in the first place? The Moon lacks an active dynamo now, but analyses of Apollo-era rock samples prove its crust holds traces of magnetism dating back billions of years. Some researchers propose that colossal asteroid impacts during the Moon's violent past could have melted sections of the crust, temporarily creating localized magnetic dynamos as the material cooled. Others point to subterranean lava flows rich in iron-rich minerals, which may have solidified in the presence of an ancient global field, preserving magnetism like a snapshot of the Moon's fiery youth. The swirls don't just sit quietly, they actively shape the Moon's environment. Recent observations show fine dust particles levitating above these regions, likely kicked up by electrostatic forces from the interacting magnetic fields and solar wind. This phenomenon might explain why the bright patches stay so clean while the rest of the surface accumulates darker debris. Intriguingly, similar magnetic deflections could be critical for future lunar bases. Strategically positioned habitats might leverage these natural shields to mitigate radiation risks for astronauts. Yet mysteries persist. Some swirls appear perfectly aligned with magnetic hotspots, while others show only weak correlations. A few even twist through regions with no detectable magnetism at all, hinting that other forces like cometary gas impacts or subsurface volatiles could be at play. Upcoming missions like NAS, a lunar vertex rover set to explore Rayner Gamma, aim to map these magnetic fields in unprecedented detail. What they uncover won't just solve a lunar puzzle, it could rewrite our understanding of how airless worlds across the cosmos weather the storm of stellar winds, leaving behind ethereal patterns as their silent testimony. Piercing closer to the Sun than any spacecraft before it, NASA Parker Solar Probe has rewritten the rules of solar physics by exposing the chaotic ballet of magnetism at work just millions of miles from our star's surface. This scorched emissary, armored against temperatures exceeding 2,500 degrees Fahrenheit, discovered that the Sun's magnetic field doesn't just guide the solar wind, it actively shreds and rebuilds it through a process scientists call switchbacks. These sudden, whip-like reversals in the magnetic field were detected as early as 2018, when the probe first dipped into the sun's corona, revealing a landscape far more turbulent than any model had predicted. One of the mission's most shocking revelations was how these magnetic zigzags accelerate particles. As the probe ventured within 15 solar radii close enough to spot fine structures in the corona, its instruments captured magnetic field lines folding back on themselves like tangled spaghetti, creating kinks that catapulted solar wind plasma to staggering speeds. Imagine a surfer catching a wave, only to have the wave suddenly flip direction mid-ride. That's the kind of chaotic environment Parker documented. These switchbacks aren't rare anomalies. They account for nearly half of all solar wind fluctuations near the sun, proving that magnetism doesn't just smooth the solar wind's flow, it churns it violently. The probe also unraveled a long-standing mystery: why the solar wind accelerates to supersonic speeds as it escapes the corona. Traditional models pointed to thermal pressure, but Parker's magnetic field measurements told a different story. Elf-vane waves, ripples in the magnetic field first theorized 8 decades ago, were caught in the act of transferring energy directly to particles. Like an invisible hand shaking a cosmic jump rope, these waves pump energy into the solar wind, accounting for much of its explosive acceleration. The data showed these waves are most intense near the Elf-vane critical point, the boundary where solar magnetism loses its grip, confirming a hypothesis that had lingered since the 1960s. Perhaps most crucially, Parker revealed how the sun's magnetic field sculpts the solar wind's very structure. High-resolution readings unveiled microstreams, narrow jets of fast-moving particles aligned along magnetic corridors, and pseudostreamers, towering magnetic loops that funnel slow, dense wind like cosmic traffic lanes. These features explain why Earth sometimes experiences abrupt shifts in space weather. Our planet often crosses between these magnetic highways where solar wind speed and density can change by factors of 2 or 3 within hours. The mission's discoveries aren't just academic, they're rewriting space weather forecasting. By mapping how magnetic turbulence evolves near the sun, scientists can now trace the origins of solar storms back to their coronal roots, potentially adding days of warning before disruptive particles reach Earth. Parker's latest orbits, skimming just 5.3 million miles from the solar surface, promise even deeper revelations about how magnetism turns the corona into the universe's most efficient particle accelerator. A relentless engine powered by invisible forces we're only beginning to comprehend. Deep within the sun's seething atmosphere, colossal tendrils of magnetism twist and wind like cosmic vines, storing energy with every turn. These magnetic ropes, bundles of intertwined field lines, represent one of the most destructive forces in our solar system, capable of unleashing explosions that dwarf humanity's entire nuclear arsenal in a single snap. When these structures grow too tightly wound, they rupture in spectacular fashion, triggering solar flares that briefly outshine the sun's entire surface in X-rays. The anatomy of a magnetic rope is both elegant and terrifying. Imagine braiding strands of an elastic band until the tension becomes unbearable. That's essentially what happens as the sun's rotation and convection stretch magnetic fields into helical coils. Each rope contains enough pent-up energy to power human civilization for millennia, all compressed into a structure no wider than Earth. NASA's Solar Dynamics Observatory has captured these formations in extreme ultraviolet light, revealing their telltale sigmoid shapes moments before catastrophe strikes. The moment of rupture defies human scale. When the ropes finally snap, magnetic reconnection converts that stored energy into heat, light, and motion at mind-bending efficiency. Temperatures soar past 18 million degrees Fahrenheit in milliseconds, while charged particles get accelerated to nearly light speed. The resulting flare can release energy equivalent to 10 billion hydrogen bombs, all originating from invisible lines of force thinner, relatively speaking, than spider silk. What makes these events truly extraordinary is how they sculpt space weather. The most powerful flares, dubbed X-class, often hurl coronal mass ejections our way billion-ton clouds of magnetized plasma that can ignite global auroras or cripple power grids. The infamous Carrington event of 1859 likely sprang from such a magnetic rope's disintegration, its unleashed energy telegraphing a warning about our star's hidden violence. Yet these eruptions aren't purely destructive. Magnetic ropes may also solve the long-standing mystery of why the sun's corona burns at millions of degrees while its surface stays relatively cool. Some theories suggest countless nanoflares, smaller versions of these magnetic snap events, continuously heat the outer atmosphere like popcorn kernels popping in unison. Recent spacecraft like Parker Solar Probe have flown close enough to sample these magnetic beasts in their natural habitat, discovering that the ropes often rebuild themselves after eruptions like cosmic hydras regrowing heads. This resilience hints at an endless cycle, twisting, snapping, and reforming that has shaped our star's behavior for billions of years and will continue long after human civilization fades from memory. Deep inside planets across the solar system, a hidden power plant hums a churning ocean of molten metal or ionized gas that transforms simple rotation into an invisible force field stretching thousands of miles into space. This cosmic generator, known as the dynamo effect, turns ordinary planetary interiors into colossal electromagnets through a mesmerizing interplay of motion and conductivity. Earth's protective shield arises from rivers of liquid iron swirling nearly 3,000 kilometers beneath our feet, while Jupiter's monstrous magnetic field draws energy from metallic hydrogen crushed into a bizarre quantum state by pressures exceeding 3 million atmospheres. The recipe for a planetary dynamo requires three key ingredients: a conductive fluid, rapid rotation, and convection. Picture Earth's outer core, a molten iron-nickel alloy where temperatures soar past 5,000 degrees Celsius. As hotter material rises and cooler matter sinks, these convection currents twist and stretch existing magnetic field lines like taffy. Meanwhile, Earth's 24-hour rotation imparts a spin to this chaotic motion, organizing the turbulence into helical currents that amplify weak magnetic fields into a global shield. It's the same principle behind a bicycle-like dynamo-mechanical motion, converted into electromagnetic energy, but scaled up to planetary proportions with enough power to deflect solar storms that would otherwise strip away our atmosphere. Gas giants take this mechanism to extremes. Jupiter's dynamo operates in a realm where hydrogen, normally an insulating gas, gets compressed into a liquid metal capable of conducting electricity. Deep beneath its colorful cloud bands, this exotic fluid spirals at speeds exceeding 20,000 miles per hour, driven by the planet's 10-hour spin cycle. The result, a magnetic field 20,000 times stronger than Earth's, with polar vortices so intense they accelerate electrons to near light speed. Saturn's surprisingly symmetrical field, meanwhile, hints at dynamo peculiarities, possibly helium rain falling through its metallic hydrogen layer, smoothing out irregularities that would tilt the field on other worlds. Even smaller bodies reveal dynamo surprises. Mercury's weak but persistent magnetism suggests its partially solidified core still hosts pockets of molten metal sloshing under tidal forces from the Sun. Mars' crustal magnetic stripes tell a tragic tale, fossilized remnants of a dynamo that died as the planet's core cooled, dooming its atmosphere to solar wind erosion. The Moon's ancient field, preserved in Apollo-era rock samples, challenges our understanding of how small objects sustain magnetic generation, with theories ranging from colossal impacts to crystallizing magma oceans. What unites these diverse worlds is the universality of electromagnetism's laws, from Earth's familiar geomagnetic field to the lopsided magnetic monsters of ice giants like Uranus. Each dynamo tells a story written in the language of spinning conductors, where the same fundamental physics yields wildly different outcomes based on a planet's composition, size, and history. These invisible engines don't just shape magnetic fields, They determine whether worlds can nurture atmospheres, deflect lethal radiation, or even potentially harbor life. As we find exoplanets orbiting distant stars, recognizing the signatures of active dynamos may prove just as crucial as spotting water or oxygen in the search for Earth's cosmic twins. Buried within the swirling chaos of a protostellar disk, the cosmic nursery where planets take shape, lies a mysterious region where the usual rules of motion break down. Astronomers call this the dead zone, a vast donut-shaped gap where gas stubbornly resists spiraling inward toward the growing star, the culprit behind this cosmic traffic jam. Magnetic fields powerful enough to put the brakes on gravity itself. At the heart of this phenomenon lies a tug of war between two forces. Normally, gas in the disk loses energy through friction, gradually drifting closer to the newborn star. But in the dead zone, located roughly between 5 and 50 astronomical units from the center, something extraordinary happens. Ionizing radiation from the star can't penetrate this far, leaving the gas largely neutral rather than charged. Without enough free electrons to sustain strong magnetic coupling, turbulence dies down dramatically. The result is a startlingly smooth region where gas moves like thick syrup, too viscous to generate the friction needed to continue its inward journey. This magnetic calm has planet-altering consequences. Giant planets like Jupiter rely on rapid gas accretion to grow, but in the dead zone, material piles up like cars on a blocked freeway. Simulations show this bottleneck could explain why gas giants often form at specific distances from their stars, right where the dead zone's outer edge concentrates drifting material. The ALMA telescope has spotted real-world evidence in disks like HL Tau, where bright rings of dust and gas align eerily with predicted dead zone boundaries. Yet the dead zone isn't entirely lifeless. While it stifles gas flow, it curiously fosters dust growth. With less turbulence, microscopic particles collide gently enough to stick together rather than shatter, building the seeds of future planets. Some theories suggest this might be how rocky cores of gas giants first assemble before migrating inward or outward to richer feeding grounds. The zone's quiet embrace could even shelter delicate ice mantles on dust grains, reservoirs of water, and organic molecules later delivered to budding terrestrial worlds. What makes this magnetic barrier truly fascinating is its fleeting nature. As stars mature, their increasing radiation eventually ionizes the dead zone, breaking the stalemate and allowing gas to surge inward in one final feeding frenzy. This may trigger dramatic planetary migrations, explaining why some hot Jupiters orbit bizarrely close to their suns. The dead zone's quiet reign proves that even in the chaos of creation, magnetism carves out sanctuaries where the cosmos can pause, gather its resources, and prepare for the next act of planetary construction. Deep within the swirling chaos of an accretion disk where superheated gas spirals toward a black hole's hungry maw, a hidden instability reigns supreme, controlling how quickly matter plunges into the abyss. This phenomenon, called the magnetorotational instability, or MRI for short, is the cosmic engine that transforms what should be an orderly orbital dance into a turbulent feeding frenzy. Without it, black holes might starve, galaxies would lack their brilliant quasars, and the universe would look radically different than it does today. The MRI arises from a deceptively simple imbalance between rotation and magnetism. Imagine a disk of gas orbiting a black hole. Material closer to the center moves faster, just as Mercury orbits the Sun quicker than Neptune. Normally, this differential rotation would keep gas parcels neatly separated, like lanes of traffic flowing at different speeds, but introduce even a weak magnetic field and everything changes. The field lines threading through the gas act like invisible springs, connecting fast-moving inner regions to slower outer ones. As the inner material pulls ahead, it stretches these magnetic springs until snap, they rebound, transferring energy outward while flinging inner material inward. This creates a runaway effect. The transferred energy stirs up turbulence, which in turn amplifies the magnetic field, creating more turbulence in a self-reinforcing cycle. Within mere orbits, the entire disk becomes a churning maelstrom where gas loses angular momentum far faster than simple friction could explain. Simulations show MRI-driven disks developing spiral arms and vortices resembling hurricanes, with material funneled toward the black hole at rates that can produce some of the most luminous objects in the universe. The brilliance of this process lies in its universality. Whether in the disk around a newborn star or one feeding a supermassive black hole, the MRI operates by the same rules. Even protoplanetary disks where planets form rather than vanish show its fingerprints in the gaps and rings sculpted by magnetic turbulence. The instability even solves a long-standing puzzle about quasars, how they can consume matter fast enough to outshine entire galaxies. Without the MRI's efficient transport mechanism, gas would orbit lazily for millennia rather than plunging inward in years or decades, yet the MRI isn't invincible. In extremely hot or dense disks, collisions between particles can dampen the turbulence, essentially short-circuiting the instability. Some theories suggest this might explain why certain black holes flicker between feast and famine. Their disks may toggle between MRI-driven chaos and magnetic silence. Other models propose that powerful jets launched along a black hole's poles could stabilize the disk in some regions while allowing the instability to rage elsewhere, creating a bizarre patchwork of order and mayhem. What makes this instability truly humbling is how it bridges scales. The same physics that governs gas spiraling toward a stellar mass black hole also operates in the gargantuan disks around quasars, spanning light years yet obeying equations fit on a napkin. It's a reminder that the universe often reuses its most elegant mechanisms, from the smallest nebula to the heart of the most luminous objects in existence. The magnetorotational instability doesn't just feed black holes. It shapes the cosmos one swirling disk at a time. Stephen Hawking once proposed a startling idea, that black holes might not be the bald, featureless monsters we imagine, but instead could possess a kind of magnetic hair. This theory suggests that even as a black hole consumes stars and galaxies, it could retain faint imprints of their magnetic fields, like ghostly fingerprints clinging to the universe's most destructive objects. The conventional view holds that black holes erase nearly all information about what falls into them, preserving only mass, spin, and electric charge, a principle known as the no-hair theorem. But Hawking's radical rethink argues that magnetic fields could leave subtle traces in the warped spacetime around a black hole's event horizon. Imagine dunking a magnet into water. Even after you remove it, the water's surface might ripple in ways that betray the magnet's recent presence. Similarly, a black hole's gravitational grip might stretch and twist the magnetic fields of swallowed stars without completely erasing them. This concept gains credibility from observations of supermassive black holes like M87's colossal core, whose polarized light reveals tightly wound magnetic structures near its event horizon. These fields behave unlike anything seen in empty space. They're concentrated, dynamic, and seemingly anchored to the black hole itself. Some physicists speculate they're fossilized remnants of magnetic energy from devoured gas clouds or neutron stars, preserved in the extreme gravity like flies caught in cosmic amber. The implications ripple across astrophysics. If black holes do hoard magnetic memories, it could solve the information paradox that haunted Hawking, the idea that matter falling into a black hole seemingly vanishes from the universe, violating quantum physics rules. Magnetic hair might encode snippets of that lost information, offering a way for the cosmos to balance its books after all. Even more provocatively, this magnetic residue could influence how black holes feed. Simulations show that tangled field lines near the event horizon might act like a cosmic braking system, regulating how quickly gas spirals inward. some observed black holes flicker unpredictably behavior that could stem from internal magnetic turbulence as new fields collide with older, haired ones. Yet the theory remains contentious. Detecting these faint magnetic whispers requires instruments sensitive enough to pass subtle variations in a black hole's shadow, a challenge the Event Horizon Telescope is only beginning to tackle. What's clear is that if Hawking was right, black holes aren't the ultimate erasers we thought. They might be cosmic archivists preserving magnetic stories from the stars they've destroyed, written in a language we're just learning to read. Tiny satellites, each no larger than a refrigerator, are rewriting our understanding of one of space's most explosive secrets, magnetic reconnection. NASA's Magnetospheric Multiscale Mission, or MMS, deploys a quartet of identical spacecraft flying in a precision pyramid formation to catch this invisible phenomenon in the act. Unlike most Earth-observing missions that study our planet from afar, these probes dive straight into the danger zone, Earth's magnetotail, where magnetic field lines stretch like overstretched rubber bands before violently snapping apart. What makes MMS revolutionary is its ability to track reconnection at electron scales, observing processes that happen in the blink of an eye across distances shorter than a soccer field. Earlier missions could only glimpse the aftermath of these explosive events. MMS's instruments sample the magnetosphere up to 100 times faster than previous probes, capturing data fast enough to freeze-frame electrons spiraling along breaking field lines at nearly light speed. The satellites orbit just 10 kilometers apart at their closest approach, a staggering feat of navigation that allows them to map the 3D structure of reconnection sites like cosmic CT scanners. One of the mission's most startling discoveries overturned decades of textbook diagrams. Instead of the neat, X-shaped reconnection patterns theorists predicted, MMS found chaotic electron-scale whirlpools where magnetic energy gets funneled into discrete jets. These structures, dubbed electron diffusion regions, act like particle accelerators, spots where electrons get catapulted to relativistic speeds while ions lag behind, creating intense electric currents. The probes have even witnessed magnetic islands, bubbles of plasma pinched off during reconnection, that drift away like cosmic balloons filled with high-energy particles. The practical implications stretch far beyond academic curiosity. Every time a solar storm rattles Earth's magnetic shield, it's reconnection that determines whether we'll see dazzling auroras or continent-wide blackouts. MMS data revealed how these events trigger chain reactions, first breaking field lines near Earth, then sending shockwaves along the magnetosphere that eventually funnel solar particles down our poles. By modeling these sequences, forecasters can now predict space weather impacts with unprecedented accuracy, giving satellite operators and power grids precious extra minutes to brace for incoming storms. Perhaps the mission's most poetic contribution lies in proving how processes around Earth mirror universal phenomena. The same physics MMS observes in our magnetosphere plays out in solar flares, black hole jets, and even distant neutron star mergers. When the probes detected Hall effect currents during reconnection, a phenomenon first described in 19th century physics labs, it confirmed that laws governing handheld electronics also shape explosions lighting up the cosmos. This tiny fleet's findings remind us that the universe loves recycling its most elegant mechanisms, from the smallest circuits to the grandest celestial fireworks. Every 11 years, like clockwork, the Sun performs a cosmic magic trick. Its north and south magnetic poles swap places in an event that reshapes our entire solar system's weather patterns. Right on schedule, the next great solar flip is due around 2030, and while it won't physically turn the Sun upside down, this reversal will send ripples of change across space, disrupting satellites, amplifying auroras, and even subtly altering how cosmic rays reach Earth. The mechanics behind this flip are as elegant as they are powerful. Deep inside the Sun, rivers of plasma churn like water in a boiling pot, twisting the star's magnetic field into increasingly complex knots. Over time, these tangled fields erupt through the surface, creating sunspots where magnetism bursts outward like springs uncoiling. As the solar cycle peaks, turbulence in the sun's differential rotation, its equator spinning faster than its poles, stretches these field lines until they snap and reorganize. The result, a global magnetic reset where the North Pole becomes south and vice versa, completing a 22-year cycle that's been running uninterrupted for millennia. History offers clues about what to expect during the 2030 reversal. The last flip in 2013 triggered a surge in space weather events, from dazzling auroras spotted as far south as Florida to temporary disruptions in radio communications. But the real spectacle happens at the heliosphere's edge, where the sun's reversing field collides with interstellar space. NASA Voyager probes detected shockwaves from previous reversals rippling outward for years, like cosmic tsunamis traveling at 500,000 miles per hour. These pressure changes can temporarily weaken our solar system's protective bubble, allowing more galactic cosmic rays to sneak inside, a phenomenon linked to increased cloud cover on Earth in some climate models. What makes the upcoming reversal particularly intriguing is how modern technology will capture it. Solar Orbiter and Parker Solar Probe will have front-row seats, tracking the magnetic upheaval in unprecedented detail. Scientists are especially keen to study how the flip interacts with the sun's tilted dipole, a slight misalignment between its rotational and magnetic axes that may influence the intensity of post-flip solar storms. Some theorists speculate this could lead to a more asymmetrical reversal, with one hemisphere leading the other by months, creating temporary magnetic chaos that might spawn unexpected space weather. Yet for all its drama, the solar flip isn't something to fear. It's a natural rhythm, one that ancient civilizations may have indirectly recorded in tree rings and ice cores showing periodic spikes in solar activity. Modern grids and satellites are better hardened against magnetic disturbances than during past reversals, though operators will still need to monitor for anomalies as shifting solar winds buffet Earth's magnetosphere. The real gift of 2030's flip may be the chance to witness our star's hidden magnetic machinery in action, a fleeting glimpse into the engine that drives everything from sunspots to solar cycles, all written in the silent language of shifting poles. Locked inside ancient meteorites are secrets from the solar system's violent birth, tiny magnetic imprints so resilient they've survived unchanged for 4.6 billion years. These magnetic fossils, preserved in mineral grains no wider than human hairs, serve as time capsules from an era when the planets were just taking shape. When scientists analyzed the Allende meteorite that fell over Mexico in 1969, they found chromium oxide crystals bearing magnetic signatures stronger than Earth's current field. How could minerals from the primordial solar nebula hold such intense magnetism? And what does it reveal about the forces that sculpted our cosmic neighborhood? The answer lies in how these metallic flecks formed. As the infant solar system's dust cloud collapsed, some grains condensed directly from vaporized gas, freezing the local magnetic field into their atomic structure like a snapshot. Others, like the millimeter-sized chondrules found in carbonaceous chondrites, melted and resolidified during ancient collisions, trapping magnetic information as their iron-rich minerals crystallized. Modern techniques using superconducting quantum interference devices instruments sensitive enough to detect a magnetized grain smaller than a virus, can reconstruct both the strength and orientation of these fossil fields. The results are staggering. Some grains recorded fields measuring over 100 microteslas, nearly twice as strong as Earth's surface magnetism today. This contradicts long-held theories about the early solar system's magnetic environment. Astronomers once assumed the protoplanetary disk hosted only weak, disorganized fields. But these meteoritic records suggest pockets of intense magnetism, possibly amplified by turbulent plasma flows near the young sun. One leading hypothesis points to magnetized accretion columns, concentrated streams of gas channeled by magnetic fields onto the growing star. These structures could have created localized zones of extreme magnetism where certain meteorite components formed, like cosmic lightning rods focusing energetic currents. What makes these magnetic fossils truly invaluable is how they chronicle planetary formation in action. Studies of the Samarkand meteorite revealed fluctuating field strengths correlating with different mineral layers, effectively documenting how magnetism varied as dust grains aggregated into planetesimals. Some grains even show evidence of brief magnetic reversals, hinting that the solar nebula experienced polarity flips akin to the Sun's modern cycles, but on much shorter timescales. Beyond rewriting solar system history, these discoveries have startling implications for exoplanets. If young planetary systems commonly host such intense, patchy magnetism, it could explain why some worlds develop iron-rich cores while others don't. Magnetic forces might have preferentially drawn metal grains together in certain regions, seeding the formation of metallic planets like Mercury while leaving neighboring orbits relatively depleted. This would mean magnetism didn't just guide planet formation. It determined the very distribution of elements across entire solar systems, yet mysteries persist. Why do some pristine meteorites show no magnetic imprint at all? Could certain minerals have erased their records over time, or did they form in magnetically quiet voids? Future missions analyzing asteroid Ryugu and Bennu samples may provide answers, comparing their magnetic histories with meteorites that reached Earth naturally. Each new grain analyzed adds another piece to an epic puzzle, one where invisible forces from our solar system's first moments left enduring marks in the most unassuming of cosmic stones. Hidden in the faint whispers of the universe's first light may lie clues to a mystery older than stars, the origin of cosmic magnetism. As astronomers push the limits of observation toward the cosmic dawn, when the first galaxies flickered to life, they're hunting for an elusive signal, the imprint of primordial magnetic fields woven into the fabric of space itself. These fields, if detected, could reveal whether magnetism predated stars and galaxies or emerged from the chaos of early structure formation. The challenge lies in teasing apart this signal from the noise of 13 billion years. Future observatories like the Square Kilometre Array, with its thousands of radio antennas spanning continents, aim to map hydrogen atoms from the universe's infancy. As these atoms interacted with ancient magnetic fields, their radio emissions would carry subtle polarization signatures, twists in the light that act like cosmic barcodes. Even fields a billion times weaker than Earth's could leave detectable scars if they permeated vast intergalactic volumes during the epoch of reionization, when the first ultraviolet light tore through the cosmic fog. Some theories suggest these fields originated in the Big Bang's aftermath, when quantum fluctuations imprinted weak magnetism onto the expanding universe. Others argue they were forged later by proto-galactic shocks or the turbulent jets of the first supermassive black holes. The telltale difference would be their coherence. Primordial fields would show large-scale uniformity, while later origins would create patchwork patterns mirroring the distribution of early cosmic structures. The James Webb Space Telescope offers another path. By studying the polarization of infrared light from the earliest galaxies, astronomers might spot how nascent magnetic fields influenced star formation. Some models predict these fields acted like cosmic scaffolding, channeling gas flows into filamentary structures that birthed the universe's first stellar nurseries. If so, the alignment of ancient dust grains or the morphology of protogalactic clouds could betray magnetic fingerprints invisible to current instruments. Perhaps most tantalizing is the possibility of discovering magnetic relics from cosmic inflation, the universe's exponential expansion in its first fraction of a second. Certain inflationary models predict the generation of primordial fields strong enough to seed all later magnetism. Detecting these would require identifying unique patterns in the cosmic microwave background's polarization at finer scales than currently possible, a task for next-generation satellites like LightBird or SIMBS-4. What makes this hunt revolutionary isn't just the technology, it's the potential to rewrite cosmology's timeline. If magnetism shaped the universe's first structures, its influence might be encoded in the very architecture of galaxy clusters and cosmic voids we see today. Like paleontologists reconstructing ecosystems from fossilized bones, astronomers could soon piece together the invisible forces that govern the cosmos long before the first stars ignited. The magnetic window to the cosmic dawn won't just show us the universe's first light. It may reveal the hidden hands that arranged its building blocks in the darkness. Even the universe has its breaking points, and magnetism is no exception. When it comes to cosmic magnetic fields, the laws of physics impose boundaries so extreme they warp the very fabric of reality. At the pinnacle of what nature permits stand magnetars, neutron stars with fields reaching a quadrillion times stronger than Earth's. These stellar corpses generate forces so intense they distort the quantum vacuum around them, creating conditions where atoms stretch into needle-thin shapes and light itself bends unnaturally. Yet theoretical physics suggests this might only scratch the surface of magnetism's ultimate potential. Beyond observable magnetars lies a realm of hypothetical extremes, conditions where magnetic fields approach their absolute limits. Quantum electrodynamics predicts a critical threshold called the Schwinger limit, approximately 4.4 times 10 to the 13th Tesla. At this point, the vacuum of space itself would become unstable, spontaneously generating electron-positron pairs as the field's energy converts directly into matter. Magnetar fields already approach 1% of this value, making them natural laboratories for testing physics at the edge of comprehensibility. Some models venture even further, proposing magnetic black holes, objects where magnetism rivals gravity in strength. While no known process creates such monsters naturally, speculative theories suggest they could form in the early universe's chaotic conditions or through collisions in higher dimensional space. These theoretical beasts would distort spacetime differently than their non-magnetic counterparts, potentially producing gravitational waves with distinct imprints or warping light in bizarre concentric patterns. Their event horizons might even develop magnetic hair, faint but permanent imprints of their electromagnetic legacy, as Stephen Hawking once theorized. The true ceiling for magnetism may lie in the Planck scale, the smallest meaningful units of space and time. Here, at energies a trillion times beyond what particle accelerators can achieve, magnetic fields could theoretically reach 10 to the 53 Tesla. At these inconceivable intensities, the fundamental forces might unify, blurring the distinction between electromagnetism and gravity. Some cosmologists speculate such fields could have briefly existed during the Big Bang's first instance, seeding cosmic inflation or imprinting anomalies we now detect in the universe's large-scale structure. Yet nature appears to enforce practical limits. Even in the most violent cosmic events, quasar jets, neutron star mergers, or gamma-ray bursts, magnetic fields top out around 10 to the 15 Tesla. This suggests unknown damping mechanisms, perhaps quantum effects or energy losses to gravitational waves, preventing fields from reaching their mathematical extremes. The universe seems to whisper that while magnetism can bend the rules, it cannot rewrite them entirely. A reminder that even the most powerful forces must eventually yield to deeper physical laws. What makes these theoretical frontiers so captivating isn't just their scale, but how they illuminate the interconnectedness of nature's forces. Magnetic fields strong enough to distort spacetime itself hint at hidden links between electromagnetism and gravity, connections that might one day unlock secrets from extra dimensions to dark energy. Until then, magnetars remain our guides to this cosmic boundary land, their twisted magnetic signatures pointing toward physics we're only beginning to imagine. From the atomic shredding power of magnetars to the delicate magnetic ballet guiding star formation, these 50 facts reveal how magnetism weaves itself into every scale of the cosmos. Think about this: without Jupiter's monstrous magnetic shield deflecting comets, Earth might have faced constant bombardment, while our own planet's geomagnetic flip-flops have rewritten the rules of navigation countless times throughout history. Even in the voids between galaxies, faint magnetic tendrils sculpt the universe's largest structures, proving that what we can't see often shapes what we can. Consider the puzzles still waiting to be solved. Why does Saturn's magnetic field align so perfectly with its rotation when other planets wobble wildly? How do protoplanetary disks maintain magnetic dead zones that later birth gas giants? And what triggered those strange zebra stripes in Earth radiation belts? For every mystery unraveled like the Sun's 11-year pole flips or the eerie lunar swirls, dozens more linger at the edge of our understanding. That's the real magic of cosmic magnetism. It's a force that connects the quantum world to galactic superstructures, all governed by the same elegant physics. Whether you're fascinated by black holes spitting magnetized jets or the way your compass twitches during a solar storm, there's always another layer to uncover. So tell us which fact bent your mind like a magnetic field warps space-time. Drop your favorite in the comments, and if you're hungry for more deep space wonders, hit subscribe. The universe has infinite stories left to tell, and we're